करो देखो चेक करो। ओ ये उधर कुछ नहीं होगा।
तो बेस में this will be here only.
First we will be here only.
Okay sir.
Then after that you wanted to move and then check.
Yes. Yes.
थोड़ा सा नेटवर्क जा रहे हैं आ रहे हैं.
एक काम करो ना
हम लोगों को
When you are moving because next day HOD के लिए होगा. ना.
Connection is
Come close so you can answer.
नॉट डेट टू डिस्कस।
First speaker invite at a partner के लिए somebody.
ठीक है ना? Connection is correct. Is there? ठीक है. इसका ये अडेप्टर
रिकॉर्ड करना है ना, इसको स्टार्ट रिकॉर्डिंग कर दूं?
हाँ लेके आओ चार्ज कर.
कहाँ पे जाएगा पता नहीं।
रहने देती हूँ
लगा के
लाइव में है तो
ये रिकॉर्डिंग नीडेड इस वेंट लाइव इट्स वेंट लाइव।
यू कैन नहीं रिकॉर्डिंग नहीं है तो लाइव स्ट्रीमिंग चलने दो, जब स्टार्ट होगा रिकॉर्डिंग कर।
ओके
यू जयपाल चेक ना YouTube.
हाँ
YouTube
ऑलरेडी
you check.
ऑन ओ एक
Going
काम
on.
ये लिंक भेज दो संजय उसको राइट क्लिक
हाँ
करके।
ये ग्रुप में थोड़ा लिंक भेज दो.
यूट्यूब पार्टिसिपेंट्स को भेजना था ना यूट्यूब का।
हाँ यस मैम
भेज दो।
पार्टिसिपेंट और ग्रुप में भी भेज दो हमारा केमिस्ट्री ग्रुप.
पूरे लास्ट रखी दो
कॉपी है ना कहाँ पे
ईमेल
भेजना?
पे भेज दो। तुम
किसको
तुम
भेजना?
एक काम करो
ओ ये खोलती
वो
हूँ
मेल भेजा है ना सबको सेंड किया है ना उसके नीचे हम फॉरवर्ड कर देंगे सबको फॉरवर्ड टू ऑल कर देंगे इधर से ही कर देंगे।
हाँ हाँ इधर से कर और ये
ओपन नहीं है
No problem.
No problem. Actually yesterday current went na
मैम
that's
कौन
why.
खोजुଛନ୍ତି कि माउस खोजुଛନ୍ତି ମୋ ପାଖରେ ଅଛି ଆଉ ଗୋଟେ नहीं ଏବେ
नहीं
यूज
मैडम करो नहीं नो इशू था ପରେ ଖୋଜିବା ଏବେ କାବଲ ଗଲେ ଗଲା କୋଟା ଆମେ ଜଏନ୍ କରି ଦେଇଥିଲୁ ବୋଲଛି ମୋ 15
I think थोड़ा close meeting है then.
एक मिनट
Mask है clear ना. हाँ.
मैं अडाची सर आ गए
ये एडमिटेड है
Adaptation is already there.
is now joined
You inform you.
Morning professor.
Yeah. Hi. Yeah. Good to see you. Yeah.
See you.
Good morning. Yeah.
Good afternoon for you.
Yeah. Thanks. Oh. So you will start from 10 minutes later?
Yeah.
Yeah.
I'll give
Okay.
a message to professor be online and then we can start. No problem.
Yes.
Sir this screen में तो not coming.
स्क्रीन में नहीं आ रहा है. ये वाला थोड़ा ये करो. इधर
ये भेज सकती हूँ ये तीनों एक भेजिए 23 से 27
इसको मत डियर आल मन करो डियर आल फॉरवर्ड नहीं आ रहा है
फॉरवर्ड ऑल है शायद इसमें मैम समस्त को फॉरवर्ड करियर अछि लिंक जे बाकी एठी तांको काली मो लिंक पठेइतले समस्त को एबे YouTube वाला पठेयर अछि तो एठी समस्त रो तो आसुनी फॉरवर्ड
ये जल देइथिलो तो ना रिप्लाई ऑल देइछो तो
हां ना दे देइछो
डॉक्टर शिवा रिसर्च लैब ताले करिबे से
हेइयो ना
जारो इंटरेस्ट अछि थ्रू दिस टीम रे एटा करो टीम रे जो मैसेज
हाँ,
है
sir,
सेथरे दे दियो
ओके हां
and if anyone is facing problem to connect through MS Team you can also watch it connect through
YouTube वो ऑलरेडी वो मैसेज
जॉइन
नहीं
मनकर जदी नहीं रहिथिबे तांको मेसेज टीम रो जनरल मेसेज रे दी माने मीटिंग रे ना
अच्छा
टीम रो जो जनरल मेसेज रे जो if you give that will pop for them
but they should join
if someone is facing network problem or something like that in MST sometimes MST is an app it won't join na YouTube will connect
because
ये chat
guys chat box में
more
नहीं,
than
नहीं.
more than 200 to need join oh now they can join I think
हाँ this is maybe maybe
just,
link we have created
just type in the chat box give the name you joining
इसको minimize
mute कर you mute everyone
हाँ yes ma'am
संध्या
yes ma'am
अच्छा संध्या ମୁଁ ଏଠି join କରି ଦେଇଛି ମୋତେ ବି ସେ ଏଥିରେ ରଖି ଦେଇଥିଲେ organizer ହଁ so that any problem ହେବେ we can use this one
yes ma'am मैम ସେଥିରେ honor ରଖିଛି ତ ଆପଣ କରିପାରିବେ ବୋଧେ
okay link ଅଛି ନା honor ଥିଲେ କରିବେ ଦେଖିବା ମାନେ ମୁଁ ମୋର ଭିडिଓ and mic on କରି ପାରୁଛି means ठीक है you have the power means okay ହଁ ଏଟା ଟିକେ ଭୁଲି ଯାଇଛି laptop ଟା सीधा
अच्छा तो ऐसे ज्वाइन कर ले मेरा नाम नहीं चैट बॉक्स में लिंक डाल दो
मैडम व्हाट्सएप में एक मैसेज डाल देते हैं हम लोग
क्या लिखेंगे तो बोलेगा व्हाट्सएप पे लिंक नहीं कर
पेस्ट कर दो
जाके भैया पूरा रहे मैडम
हाँ so you should
ये
go there
लेके जाए आधा से जाए
yeah नहीं से आना चाहिए
ये तो आ गया ये यहीं पे चला गया
हाँ ठीक है उसको उसको इंटर करके
हाँ
राइट तो
बहुत स्लो हो चुका है
ये is about to start gets the order that's always equals the order and speaker
facing those who are facing problem those who are facing problem
हेलो इधर केमिस्ट्री डिपार्टमेंट के पास आ जाओ
अरे ये इसको बोलो यार
ये प्रियंका है इधर किधर बैठ गई रे
लेकिन ये जो स्क्रीन में जो आ रहा है वो एवरीवन के लिए
मैम एक्चुअली शी वेयर शी
चल ठीक अच्छे केटा सुदेश जोनी YouTube रे एक्चुअली एटा हम YouTube रे चलते तो दोस्त लोग कैसे प्रॉब्लम टू जॉइन एमएससी प्लीज कनेक्ट लाइव प्लीज जॉइन प्लीज सी दिस कौन कोई YouTube रे देखे
through this
लिंक
link to
कनेक्ट है हां
to this link to join in the YouTube channel.
It's when you join. I just call
ठीक है ना
हाँ yes
ट्रेन से इधर जाके बैठ गई थी
फिर वैसे
क्या उसको कुछ दिया है क्या
फिर एक प्रोफेसर उधर देख रहे हैं
लाइव चल रहा है सामने बैठे चल
एक प्रियांशा को वहाँ से
सेवा को
कॉल करो हेलो अरे इधर लाइव चल रहा है तुम उधर मत बैठो बैठो
सामने से
उधर सामने बैठो
कहते कि पता नहीं
She is not sitting only when she is doing like some. She is checking her pencil.
कैमरा दिख रहा है all of you please put your phones on mute okay अच्छा तो लेजिंग है वाइब्रेशन ठीक है
सब ठीक ठाक चलছে ना
सब लोग बुला के लाएंगे और
बिल्कुल इच्छा नहीं थी नंबर पे पहले का संगठन पढ़ा हुआ कि
दूसरे ही कॉल कर
इवन आईपैड नहीं नॉर्मल टैब यूज होता है आईपैड हला नहीं होता से मैं हला से स्टार्ट बटन के तार सब उल्टा ऑपरेशन उल्टा हमर जे तले बैक करथला नहीं तार ऊपर अजेंडा ऊपर थिला से तले थिला सब उल्टा ये बुझले हो चल मम्मी ने वइस नहीं कहते चल है ना अच्छा मुझे फोन के नहीं ने बाद तुम तो इतने कनेक्ट कर से ने बोले आबा की नहीं देखबी नहीं सेने उन्हें नहीं नो मल्टीपल डिवाइस से इटा इको सेटेलाइट तो समझा के ना बस ओके समझा वी आर देयर हां एनी प्रॉब्लम यू कॉल एनी ऑफ
हाँ yes
or if you face problem anything here you go directly there
okay ma'am okay
it's already connected in the Wi-Fi
yes ma'am
so any problem if connectivity problem you go there
okay
mask normal
ठीक ଅଛି लैब रे सब कहि तो
କେତେଟା ମୋଟରେ ପଡିଥିବା ଯେ ମୁଁ ବି ସବୁ ବ୍ୟାଗରେ ଗୋଟେ ଗୋଟେ ରଖି ସେଠାରୁ ପୁରା ଭୁଲି ହେଇଯାଉଛି ସେ ଫାଇଟା ଅଛି ଓପନ ନେଇ ହଁ ନେଇକି ଅଛି ଯେ ଇନେ ଥାଉ ଇନେ ଗୋଟେ ଇନେ ଥାଉ ୱେଷ୍ଟ ମାନ ଲାଗି कम बोतल अच्छे गुडेटा अच्छे खाली हां तेले केमिति सेटा हम गोटे बोतल नेजी अच्छा
ये फिर भर
पानी टिके नहीं आसीबो हां हां काहे कि शिवानी प्रियदर्शिनी का है ओई शिवानी ये शिवानी है सेटा प्रियदर्शिनी दुई जन पर बहुत कंफ्यूज है ओसे नहीं कान चेक ओसला
वही बैठ जाओ
पूरे देखा कितनी ओके यस
अच्छी क्वांटिटी
चल कांटे की खाई दे अच्छा बिस्किट खाई दे बिस्किट खाई दे
आई दे
प्लास्टिक जगह दे
सॉरी शिवानी सेकंड फ्लोर रे भी थिला
जाने माने हठात मते
मने पड़ला से तो हटो मते
मु सेठी की बोलली
हां मुझसे भाबुतले होगन तक
माइक क्यों बंद हो नहीं रहा है?
हेलो मैम हेलो मैम
यस संध्या
हाँ ठीक अच्छे मैम शुभुची भलसे ना
एबे ठीक अछि
हाँ हाँ
हां
यस मैम
आउ डिस्प्ले टा ठीक अछि ना
आज्ञा मैम
सीट रे बसते दिखाई अछि रे
यस मैम टिके लेफ्ट साइड को करन तो पूरा टा देखा जा हाँ 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 आउ टिके आउ टिके आउ टिके मैम
तीनटा को मैडम
आउ टिके
अरे ठीक स्टेज रे
हाँ ठीक अच्छे मैम ठीक अच्छे
देखाइला
हाँ हाँ
ठीक
yes
अछि
ma'am.
ना
एफ टा
हाँ
कटि जाउची एफ टा फ्रंटियर रो एफ कटि जाउची बाकी सब ठीक अच्छे हाँ हाँ नाउ इट इज ओके मैम नाउ इट इज ओके
ओके
हाँ हाँ ଏବେ ଖାଲି admit କରିବାର ଅଛି ଆଉ କିଛି ଭୁଲ ନାହିଁ ଏଟା ବହୁତ ସ୍ଲୋ ଚାଲିଛି ଏଠି ଲାଇଭ ଚାଲିଛି
जी भी जॉइन करिवे
ଖାଲି admit କରିବାର ଅଛି
संध्या
आज्ञा मैम
वॉल्यूम टा क्लियर अछि ना
यस मैम पूरा क्लियर अछि ठीक अछि
ओके
यस
एटे सनकर ना देखो छी माने सर ग्रुप लेके
नहीं सार को कंप्यूटर रे एटा चलछि
अच्छा अच्छा
आ एठु मु ऑन करछि
सार को
तो
कंप्यूटर
एबे
सेटा यार
ऐश्वर्या सार कंप्यूटर रे सब सब ना
फॉर्मल लेटर कह देले दूसरे से कहले हम तुम माने खरा
ठीक अछि
ता टाइम में भी मिलेगा
के हमें भी को जाओ ओहो ये तो अब करियो ना हां के जब हम खड़ा तो फ्री टाइम अछि तारा चिंता नहीं हम करियो टिके तो खाली आसी जीवार बोले टिकेट खाली आसी जोर भलो ना न आसले भलो बहुत छुआ हो जाउछ हेबे बहुत छुआ बहुत जन को अछि विशाल 9:45 रे स्टार्ट छुआ सेठी अछन ना हां
यस
यस
पचरे देखे कि अछि
भावना को फोन खराब देखो अच्छा हाँ 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 ସେଇଥି ପାଇଁ ହିଁ ମୁଁ କହୁଥିଲି ହଉ ହଉ ଠିକ ଅଛି କିଏ ଯାଇଛ ଆଚ୍ଛା ଠିକ ଅଛି ସମସ୍ତଙ୍କୁ ଡାକ ଏଟଲିଷ୍ଟ 30-40 ହବା କଥା ଆଉ 10 ମିନିଟ୍ ଅଛି ତ ओके हाँ एचओडी सर का ही है अच्छा अच्छा ओके ओके ठीक है और रख लिया रख लिया हमारे कोई सेंड बाय चांस समस्त डाकी
तमे दी जण एठी रहइबो
आज्ञा मैम
आ जे आसले भी ताको पठेइबो
पठेइबो यस मैम
एक्चुअली खाली लागुछ तो
आसीन कि हेलो सेनेट हॉल आसीन ओहो अच्छा 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 ठीक अच्छे आउ के अच्छा तो कहली समस्त कहले हाँ मु जानी जे हाँ हाँ से तो जिबे तुम माने आउ को छुआ को भी कहता ना पूरा खाली खाली अछि ना एटलीस्ट 40 टा पीपल हबा कथा ना ठीक अछि तमे आसी आइथा ना पिले से एडमिट करिया काम अछि तोर हाँ लैपटॉप आनछु ना ठीक अछि रखु छी हां कौन पे कि मो यारे दीटा काम करछि ना माने यारे YouTube एटा भी देखिया रहछि आ ए तो केते एठी के आसी कि मते पुणी करिया पड़छि सेति मैं कहउछि तम पाखे रखि थाओ से ढाणी कि ना बेटर होगा ना जे किंतु कनेक्ट केमते करियो नेट भी तो दरकार
एठी गोटे ही कनेक्टर अछि ना
ना ना एठी खाली बहुत गड़बड़ हैला तो किछ आउ आसिलानी
हम्म
तो सेति में से एटा कनेक्ट कर देछन YouTube करे ना ठीक अच्छे मोबाइल रे तो आसले एडमिट कर देबी किंतु म्यूट करथा म्यूट करी खाली आसीबो आसीबो हां करवार अछि दीदी ना मैम कहले जे एठी आसी समस्त शेयर पठो एठी कर मोबाइल ताले हां हां ठीक है
ये की है
अरे वीडियो अगेंस्ट सब मैंने ही जान को हम कहले ठीक है हम खाली एडमिट करिया
हेलो हाँ तापसी अरे तू केमिस्ट्री ऑफिस देखी छु ना केमिस्ट्री ऑफिस रो सीधा जा
श्री कॉफी
देखी छु ना फास्ट
जस्ट श्री कॉफी गला गोटे बड़ रूम टे सेट सब लोक माने ठिया जंदे देखे
श्री से भीतर को बस बड़ हॉल भीतर को सार माने अछि सेठी ना हम सार अछि
से ठिया ही सर को
हम माने अछु अलग जगह रे तू हेठी बस
तो सर
अरे एका नहीं प्रियदर्शनी
समस्त
समय
अच्छा
भावना
से
सेठी
हम
अछि हमको अलग काम दिया है हाँ से केमिस्ट्री ऑफिस आसीबो तापर सीधा जीवो राइट साइड तळको ओले
Good morning, Professor Adachi, Professor
सेटा
Wong.
ई साइड रे अछि बड़ हॉल टा फ्रंट वाला हॉल
Yes, yeah. Good morning and
Good
good
morning.
afternoon. Yes.
Yeah. Good morning, Govardhan Podalla. Yeah, maybe you have to unmute your mic, Govardhan. Yeah, Professor Adachi, how are you? This is Justin from IIT Roorkee Chemistry Department.
Oh, yeah. I'm fine. And yep. So the weather is now very good. We have a sakura season and beautiful
Okay.
flowers. Yes.
श्री कॉफी से फर्स्ट
Yeah, it
श्री
will
कॉफी
be
से
really
बताइए
nice at this time in Japan and
Yeah.
even in Taiwan also. I think this is a very nice time.
Yes.
Hello, sir. Happy to see you after a long time.
Yeah, very nice to see you. How are you doing, Babu?
Yeah, everything is going good, sir.
Okay, okay. So your boss will be joining in the 12 hours today.
Yeah. Here the time will be around 2 after
2.
lunch. Probably.
Okay, yeah. So I think Professor Wong is also there. He has also joined us. Professor Wong.
I think.
Good morning, Professor.
Ken
Ken Wong.
Your office is your office same or anything change?
No, this is a new office. I have moved down now. I am in the middle floor, just in the HOD office side.
Oh, okay. Oh, got it. Yeah.
Yeah. So I think that this was an MTech classroom before. It is converted to a office now.
Okay, sir.
Yeah, we have done a lot of changes in the department. So this is one thing. So I have got a new room in the same lobby.
That is so good, sir, because I remember when I was in PhD, there was so problematic for the space.
Yeah. So we have converted a lot of classroom into a research lab as well now.
That is so good, sir. How is going your research?
Yeah, last 3 years was little difficult time for me because I have to give more time to administration.
Yeah.
But now we are coming back to track. So we are venturing into new areas. Now we are mainly working on organic transformations using, photocatalyst.
Oh, welcome,
Yeah.
sir. Yeah, right now mainly I'm focusing on Fortran Carroll based photocatalysts
Okay.
for hydrogen evolution, CO2 reduction.
Okay.
Yeah.
But we are mainly interested in simple organic transformations. And
Yeah.
currently we are, working more on the radical generation using photocatalyst.
Yes, sir. That is also very nice area.
Yeah.
But my boss is working on several research areas like OLED, photocatalysis,
Okay.
biology.
Yeah. I know. I have seen that, because, you.
Multidisciplinary, very
Yeah.
big.
Very big group. So it will
Very
be.
big.
Yeah. Actually, we are very much thankful to Professor Adachi, Ken Wong, and your supervisor because I know that they are all very busy, and then giving time to this kind of event will be very difficult for them. But
Yes,
they have kindly agreed to come over here
yes,
and
sir.
then be as a guest and as well as a speaker in these events.
Yeah,
Yeah.
it's a great pleasure.
That is so good.
Yes.
Yeah, we are waiting for the of NIT to join. Maybe he will be joining soon.
Okay, sir. It looks we are getting old, but you're still looks like young.
Hmm.
Hello.
Maybe it is partially hereditary. See, be happy always. Then you will look young.
Yeah, that is also one criteria.
life will have always ups and downs. And then when there is, down, we have to be, managing it in a very nice way, not worrying too much.
Yeah, yes, sir.
के बोलছে मरने के ଗୋଟେ ମିନିଟ୍ हेलो हाँ मैं कह लैपटॉप पठे दे और कोरियर ने पठे दे बाकी तू एले पठाबो तू एले हाय भुवनेश्वर आसु पठाबो
Good morning, Professor Siva.
Good morning, everyone.
नहीं मैं ये
So,
वो क्या मैं देखे दे
before we start this program,
नहीं आगो
now request Professor Priyabrata Das, HOD Chemistry, to welcome Professor Uma Mageshwar Rao, Director NIT Rourkela.
हैं
Oh yes.
नहीं नहीं हमर पाखे अछि ना पाखापाखि केते किलोमीटर हवा 1.5-2 किलोमीटर हवा
Now I'd like to welcome all of you. Good morning, one and all. We are happy that we, Department of Chemistry, NIT Rourkela, and jointly with Department of Chemistry, IIT Roorkee, organizing a webinar on frontiers in organic electronics. We are delighted to get encouragement and support from our Honorable Director, Professor K. Uma Mageshwar Rao, as well as Professor Ajit Kumar Chaturvedi, Director IIT Roorkee, for conducting this event. We are fortunate to have an eminent personality in the field of organic electronics, Professor Adachi, QC University, Japan, as a guest of honor. We are also happy to have Professor Das, Air Department Chemistry, NIT Rourkela, and Professor Justin Thomas, Air Department of Chemistry, IIT Roorkee, on this event. I welcome you all the exciting world of organic electronics through this webinar. Organic electronics is an emerging research area which is not only important for academics, but it is also frontline area of research and the development of semiconductor industry in display and lighting technology. Even though generation of OLEDs have already reached the 4th stage, still there are several limitations that need to be addressed. We believe this platform will certainly bring the organic electronics community together to motivate the young generation to pursue research and take this to the next level. With this, I welcome you all again to this 2 days webinar. Thank you so much. Now I request Professor Das, Head Department of Chemistry, to speak few words about the Department Chemistry and NIT Rourkela.
Okay, thank you, Professor Shiv Kumar. A very good morning to all of you present here. First of all, from the Department of Chemistry, I would like to welcome all the persons who are present here to this 2 days international webinar on organic electronics in association with Chemistry Department of IIT Roorkee. First of all, I would like to thank our director, sir, Professor K. Uma Maheswar Rao. Despite his busy schedule, he has given his consent to attend this event. So from the department side, we'd like to thank you for attending this event.
Thank
I bid welcome to all the experts and delegates who are present offline as well as online here, who despite their, they took out their time to give a nice presentation during this two-day webinar. We appreciate your efforts, sir, and we really privileged to have you in this 2 days webinar. Thank you, sir. I would like to thank also the head of the Department of Chemistry, IIT Roorkee, who gave his time to attend this event. And with the convener, Professor B. Kumar, they have arranged such a nice event, which will showcase the emerging areas of frontiers in organic electronics. On this event, I would like to tell that our department has been organizing such event in the last 2 years. The first one, which held in 2021, it was on national level. So this year we moved a little bit one step ahead and we did at the international level. So in this regard, I would like to thank the conveners, Professor B. Kumar, Professor Subudhi, Professor Patel. Despite the odd times we had in the last 2 years, they have arranged such a nice webinar. And from my core of my heart, from the Department of Chemistry, I would like to thank the conveners for arranging such an event. When I say organic electronics, the things which comes to my mind is the display. Right now, wherever I'm sitting, it's the display screen, right? So as Professor Siva Kumar told, it's already 4th generation OLED we have, right? But having said that, there are a lot of obstacles which the scientists and engineers are facing. And I believe this 2 days webinar, where we have the leading expert from all over the world, will highlight those challenges we are facing and also will showcase the methodologies how to overcome those challenges. In this regard, I believe this webinar will be a very fruitful event for those who are working in this area. Regarding my chemistry department, I like to tell that we have been organizing such seminars, workshops, conferences regularly. Just we finished this from April 12th, sir. We have another workshop on BRNS support radioisotope methodologies. This will be a 5-day workshop. So we are constantly engaged ourselves in, motivating our students, and our faculties are involved in interdisciplinary research and collaborative research, and we do these sorts conference and workshops. My department, since its inception in 1961, has become one of the biggest department, from a small department, one of the biggest department at this time. We have currently 22 regular faculties working in different areas of organic, inorganic, physical, analytical, computational. All the major thrust area of chemistry, our faculties are working. And currently we have 110 regular PhD students, sir, which are highest in the institute. So that showcases that our faculties are involved in doing quality research as well as imparting quality education to our students through their, teaching methodologies. Through the constant support from administration, sir, and also sponsored agencies, our department has been equipped with multiple high-end instruments like single crystal XRD, HRMS, surface area analyzer, CSS analyzer, flow cytometry. You can name most of the important NMR, most of the important techniques, characterization instruments we have in our department. Our faculties also, through their hard work, they got multiple sponsored projects. Sir, on this occasion, I would like to highlight that the last 3 years, our faculties have been successful in getting almost 40 sponsored projects worth around 11 crore. So this is a remarkable achievement by our faculties. And with our constant motivation by our director, sir, we are in the process to have an advanced research center where multiple state-of-the-art instruments will be there, and which will promote research in healthcare, energy, and other challenging area of research in the future time. With this, I'd like to welcome all the delegates and experts who are present here. Our guest of honors, Professor Tagachi, who is there from Kaisu University. So we welcome all, and I hope this 2 days webinar will be a fruitful one. And from our Department of Chemistry, Again, I would like to thank for accepting the invitation from the conveners and presenting in this webinar. Thank you all.
Thank you, Professor Das, for your nice appreciation and nice words. And now I will welcome Professor Justin Thomas here, Department of Chemistry, IIT Roorkee, to speak few words to the audience.
Thank you, Professor Siva. Thank you very much for giving me an opportunity to speak few words in the inaugural session of the webinar series. I would also like to take it a pleasure to invite all the delegates and audience to this webinar series on organic electronics on behalf of myself as a convener, as well as on behalf of the Department of Chemistry at IIT Roorkee to this event. And organic electronics in India is growing ever since, its inception in the world itself. And luckily we are today having with us Professor Adachi, one of the authority in organic electronics, and he will be the one who will be giving the first lecture. And he will be able to enlighten us on the developments in organic light emitting diodes and its developments and future directions. And I would like to say that this event could happen mainly because of the efforts that was put by Professor Siva. And every day I used to get a call from him saying that, we have to do this, because in India, our material chemistry mean that it is a nanomaterial chemistry, and then organic material chemistry is not getting much attention. And he was instrumental in, forming a forum in the beginning in WhatsApp level. And then we are now developing it into a forum at the national level. I congratulate Siva for his efforts. And because of his efforts, now we are having this webinar series. And at the same time, I would also like to acknowledge the support we have got from the administration at IIT Roorkee, particularly our director, Professor Ajit Chaturvedi, for his encouragement. And also I would like to put on record the support we have received from the administration from NIT Roorkela, and particularly for Professor Rao for gracing this inaugural session despite his busy schedule, and then he just took over as the director of NIT Roorkela, and we thought that he may not be able to make it out for this inauguration, but he has kindly graced this function. We are very much thankful to you, sir. And I would like to also take it as a pleasure to introduce Department of Chemistry on this occasion at IIT Roorkee. And we are having a strong strength of 28 faculty members working on different areas of organic, inorganic, and material chemistry. And our department is very strong in material chemistry. We are having nearly 10 faculty members working on this area. And then we are also having facilities required to do high-end research in material chemistry as well as in other areas of interest. And recently we have inaugurated, we are going to inaugurate on 4th of April, a laser spectroscopy lab where we can be able to do very high-end spectroscopic measurements such as transient absorption measurement and some frequency measurements. And I would also take it as an opportunity to share some important developments in our department. We have been constantly doing webinars and offline conferences in the last 2 years. COVID has helped us in one or other way to conduct online classes as well as online webinar series. In the last years, we had conducted at the Department of Chemistry IIT Roorkee 4 series of webinars. showcasing our own alumni and friends of IIT Roorkee. So there are several events we have conducted. It became a grand success. I hope that this series would also become a grand success, and we are having a very top rated scientist, international scientist as a speaker in this event, starting from Professor Adachi, Professor Ken Wong, and Professor Raymond Wong, and Professor Park, and Professor Datta, and so many other speakers are joining with us. I would like to thank all of them for agreeing to be part of this event. Though we would like to have them physically interacting with our audience, but the time is not yet conducive for such an occasion. We hope that we will be able to have soon and physical mode of interaction with the community working on organic electronics. And I hope that this event will help the people to understand the intricacies of organic electronics and then the possibilities one can explore in organic electronics. And we are taking it as an introductory, event for the people, so that people can appreciate the development possible in organic electronics in Indian side. Okay, with that, I would like to, once more thank Professor Rao for joining this meeting, and also like to thank, and I hope that everyone will have a wonderful time. Thank you all.
Thank you very much, Professor Justin, for your nice words and then introducing about the organic electronics to the community. And now I request Professor Uma Mageshwar Rao, Director Sir, NIT Rourkela, to address the gathering.
Professor Adachi from Kyushu University, Professor Justin Thomas, Head of the Department, IIT Roorkee, and Professor Das, Head of the Department Chemistry, NIT Rourkela, and Professor Shivkumar, convener of this webinar on frontiers in organic electronics, and Professor Shivkumar and various other faculty members of the Department of Chemistry and the research scholars. A very good morning to you all from NIT Rourkela. Rourkela, just yesterday I just got to know the meaning of Rourkela. My mother tongue is not Odia. Right, I just it's like owning. It's my city, my town, or my village. Means I belong to this place. That is what is Rourkela. So now I welcome you all to the webinar from NIT Rourkela. So now that you all belong to Rourkela. Right. So now having said this one, it gives me immense pleasure to be present here addressing the young minds out here. I'm really concerned about the young ones because that is the future that we have on my left side. Right? On my left side, they are going to be on the forefront to lead us from the front for the various areas of development that industry is really taking us to. You all know that you must have read and heard and that are facing or enjoying the revolution that has taken place around us. Industry is already in the 4.0. And then the positive aspect of COVID is that life has not really stopped. Life has evolved into a different dimension. And every single aspect of that one, which really confines or which really makes a society, has really realized the importance when there is a challenge. It is when there is a challenge that the leaders come out of the challenge, and then they have given us a new way into really make the society run, make the society move through. Okay. So now here, I know that chemistry is all about organic chemistry and the physical chemistry. And then now I'm really realizing that material chemistry, it is you are already venturing into electronics. Electronics is there all around us. It is not just only in the S, P, D, F orbitals that electrons are there, the loose electrons are moving around. And then I think the chemists have really caught those electrons and then made QLEDs and then LEDs, OLEDs, and then life is really opening out into various frontiers of its development. Now, coming to I don't want to really speak about the importance of the organic electronics, right? The experts are there, and then particularly when Professor Adachi is here, who is the authority in organic electronics. And my only point here, which I would like to address the young brains out here, is that a webinar is not just for the sake of trying to have an interaction with the people around the world. It is to exchange the ideas, right? It is to showcase where you stand, and then what exactly are your achievements. And then maybe if you have really had one publication in which 10 points are the things which you are really projecting, 9 may not really take the attention of anyone, right? One must be taking the attention of somebody out there at the corner of the world, right? That gives you the immense happiness that I could really make my one observation realize that it takes the importance of people around us. This is one opportunity for the young minds to really showcase your talent, showcase your skill, showcase what exactly you have really achieved in all these years. Right? It is just a simple motivation. Right? This is number one. Number two is that when you are hearing to that one, it's not that after the inauguration we just disperse, have tea, and then just all over. It is not just limited to the speakers to really be around the webinars or the seminars. Right? Please remember that. Ours is a country where we are trying to develop and then evolve into a completely developed country. In that era, in that stage, every single minute and every single rupee and every single occasion is very, very important for us. This is one occasion where can you really think that you will be making your presentation before Adachi? Or you get an opportunity for you to listen to him? And then where exactly is the organic chemistry or this one, organic electronics is really being really handled in Japan and various other universities? And then where are we? It gives us absolutely an opportunity for us to place ourselves in that. So now I expect my young faculty members or the young research scholars and then the others to put your time. Don't waste your time of these 2 days, and then make yourself available to be listening to the people, listening to the experts. And then you may really find 1 or 2 points which are more important to you or inspiring to you and then motivating to you. And that's where a webinar or a seminar or workshop or whatever it is, and it becomes successful. This is one. And number two is that life is not really stopping, that in spite of the mask that we are wearing and then removing the mask, and the life is going on and on and on. Right? COVID for somebody, it is a challenge. COVID for somebody, it is a curse. COVID for somebody, it is an opportunity. Right? For us, the researchers, it is a challenge as well as an opportunity, right, to give our best minds. Okay, wish you all the very best, and then make use of these 2 days webinar, and then try to bring out. I think I really know little about organic electronics. All that I know is that when I was really out in the market to find out what is the best TV that I can really purchase, it said that Sony has QLEDs, Sony has OLEDs, LG has this, LG has that. So all these things are there, but then right, I'm still to really realize as a customer what exactly is the difference between QLEDs and then OLEDs. Like just now, Professor Vaidyanathan Shivkumar said that that it has a flat display and then it's all that one. Okay, so now I wish electronics will give us even much better comfort, and then the energy is one thing. I really want that the consumption of energy, right, should be less in whichever the frontiers that we are really developing into. Okay, I wish you all the very best. Right, thank you very much.
स्पॉटलाइट मुझे नहीं पता, मैं देख रही हूँ वो स्पॉटलाइट में क्या होता है स्पेसिफाई, मतलब ये जैसे हुआ नहीं, ये जैसे हुआ सर.
Thank you, Professor Uma Maheshwar Rao, Director Henry Rourkela, for your nice words and encouragement, constant encouragement. And we look forward to have such a encouragement throughout your tenure, sir. Now I request Professor Adachi, QC University, to address the gathering. Professor Adachi.
Yeah. Can you hear my voice? Okay. Yeah.
Yes, Professor. We are listening.
Okay, yeah, good morning and good afternoon. First of all, I'd like to thank to the organizing committee for giving us a chance to talk, this nice webinar. It's a little bit pity I couldn't visit your country, but instead, so I'm happy to give my talk. So okay, so I'd like to share my slide. Yes, this one. So yeah, I want to share the statistics of the activity in organic electronics and also the OLED. So here you can see I just summarized the statistics from a Web of Science. This is the summary of published number in organic electronics. So when I was a student, before 1990, almost no almost no activity of organic electronics. And so you can see a slight increase of the number of the papers. And actually in 1997, first OLED product was commercialized by Japanese company, the Pioneer company. It's a car stereo in a carrozzeria. It's showed a very beautiful picture. So this was the very first product. And after 2000, you know, the phosphorescence OLED was appeared led by Professor Steve Forrest and Professor Mark Thompson. And so you can see a significant increase of the OLED paper. This is mainly by phosphorescence OLED. So simultaneously, very first journal, Organic Electronics, was established in 2003. So, and then 2012, you can see a further increase. So 2012, we reported the very efficient TLF-based OLED, actually showing the 100% electron photon conversion. It's an ideal device. And so recently, more than 1,000 papers per year. So lots of papers, organic electronics. Okay, so second statistics is the number of papers and the citation of the TDF. So the blue line shows the worldwide published paper related to the TDF. Actually, so after 2012, many TADF papers appeared, and recently more than 500, more than 600 paper was appeared. So very active research area TADF is. So today I'm going to talk about how we found the TADF, and then I also want to talk about the cutting edge technology of TADF. Okay, this is the third statistics is number of papers for the OLED. So you can see a significant increase after 2000, and recently around 500 or 600 papers. I also divided into the Japanese activity and worldwide. Unfortunately, Japanese OLED activity is slightly decreasing after 2006. It's a little bit pity, but not only OLED, researchers also focus on solar cells and other research areas. So finally, I'd like to show the unique. I'd like to talk about the key issue of organic electronics. So the key issue is the CT, charge transfer interactions. So you know, TADF is basically composed of the donor and acceptors. So carbazole is the donor and the cyanobenzene is the acceptor. So TADF is composed of intra or intermolecular CT. And we also reported the long persistent luminescence. We mixed electron donor and acceptors, and we control the ratio of the both materials. And we found that at the proper condition, we have a charge separation of hole and electron, and separated charge carriers recombine again, but the lifetime is quite long, almost 1 hour. So very long persistent luminescence we could realize. This also used the CT interactions. So you know the charge generation layer in OLED, it was reported by Professor Kido he stacked two OLED layers. Between the first and the second OLED, we have a charge separation, charge generation layer. So by application of the voltage, we have a generation of hole and electron at this interface that allow the multi-layer structures. And also this is a OSC. OSC, after the light absorption, we have exciton formation and exciton separations, generating the free charge carriers. It's a opposite direction. Yes.
Could you please full screen? Can you make it? Is it possible?
Yes. Can you see?
Yeah.
Okay. And okay, final one is the spontaneous polarization of dipoles. So in organic films, okay, we use the amorphous films, but amorphous film is not the random orientation of dipoles. Actually, the dipole was discovered to show the spontaneous polarizations. So after OLED fabrications, Professor Holmes disclosed that some of the molecule inside of the organic show the spontaneous polarization that induced various photophysical issues even without application of voltage. It's quite interesting. The PLQY goes down because of the charge separation happened because of the internal spontaneous polarization of dipoles. So many issues happen inside of the organic devices. So I'd like to give a message. Give you a message that the CT interaction is the heart of the organic devices. Okay, thank you very much for your attention. And yeah, I'd like to finish my greet.
Thank you, Professor Adachi, for your valuable time. And so now it's time to read a vote of thanks for the inaugural session. It gives me immense pleasure to extend vote of thanks on this occasion of 2 days webinar on Frontiers on Organic Electronics 2022. First of all, I would like to express my heartfelt gratitude to our Honorable Director, Professor K. Uma Mageshwar Rao, for providing his valuable time out for his busy schedule for this inauguration session. We are also thankful for his encouragement and continuous support in conducting such outreach program to promote science and technology and place NIT Rourkela in the globe academic map. We are also thankful to Professor Ajit Kumar Chaturvedi, Director IIT Roorkee, for his constant support and then encouragement. We are very much grateful to our eminent speakers and guest of honor, Professor Adachi, QC University, for accepting our invitation to share his scientific knowledge for promoting the research in the area of organic electronics and also to spare his valuable time to grace this occasion, inaugural function. We are also thankful all the other eminent speakers, Professor Wong Raymond, Professor Katie Wong, Professor Data, Professor Caroline, Professor Parameshwar Iyer, Professor Park, and so on. So speakers for their giving valuable time to address this organic electronics forum. We are also thankful Professor Priyabhadra Das, Head Department of Chemistry NIT Rourkela, and Professor Justin Thomas, Chairman of the convener from IIT Roorkee and Head Department of Chemistry IIT Roorkee, for their continuous effort and support to make this event successful. We are also very much grateful to our eminent speakers to accept our invitation to share their scientific knowledge, promoting research in the area of organic electronics to ignite the young minds. We very much thankful to our department faculty colleague as well as the faculty community NIT Rourkela to support their continuous support and inspiration for conducting such an event. We are also thankful our supporting staff and students for their timely help and cooperation. And we also extend our thanks to Mrs. Archana Gupta, Public Relation Officer, for her effort to publicity as well as support to this event. We are very much thankful Manish Ogde, Head CC and Computer Center technicians, etc., to support this event. And I wanted to also highlight, in line with the Professor Justin, who was the one who has said 5 years before that we should have some kind of forum that where we can able to interact among our national community in the frontline organic electronics people. We are chemists. We always hired making molecules, but we don't have support to make a device. We always look for the kind of we make thousands of molecule. I mean, one PhD thesis consists of 400 molecule, let's say, but we have we need to have such kind of support from the people around the physics and materials scientists or engineers to make a device for us. We are fortunate enough. Professor Ju is supporting us. Many groups in India. Professor Zhu, National Tsinghua University, Taiwan. And I also thank Organic Materials Forum or Organic Electronics Forum India, Professor Jayabharati Annamalai University, Professor Ajay Perumal from IISER Perampur, Professor Rajamalli from ISC Bangalore, Professor Achal Kumar from IIT Guwahati, Professor Suprata Ghosh from IIT Mandi, Professor Parameshwar Iyer from IIT Guwahati, Professor Satish Patel from ISC Bangalore, and so on and so forth. So many people are now getting into this organic electronics. Finally, we are glad for the overwhelming response from the participant to make this objective of the webinar successful. So thank you very much for kind attention for this inaugural session. Thank you so much. Okay, done. Okay. So wish you all the very best. Okay, thank you. So we will be able to meet after 10 minutes, 10:30 exactly, for the Professor Adachi talk in this forum platform.
ଠିକ ଅଛି ଶିବାନୀ ସାର୍ଙ୍କର ତ ଦେଖାଯାଉଥିଲା। କଣ କହୁଥିଲା କି ସେ କହିଲା ସାର୍ଙ୍କର ଟିକେ ବଡ କରିଦେ ଆଉ ଜଷ୍ଟିନ ସାର୍ ଦେଖାଯାଉଛି। ମୁଁ କହିଲି ନାଇଁ ସାର୍ଙ୍କର ତ ଦେଖାଯାଉଛି।
ଆରେ ମାନେ ନେଟୱାର୍କ ପ୍ରୋବ୍ଲେମ ପାଇଁ ନା କାହାର କେତେବେଳେ ଗୋଟେ ଲେଟରେ ଆସୁଛି କାହାର କେତେବେଳେ ଗୋଟେ ଜଲ୍ଦି ଆସୁଛି।
ଠିକ ଅଛି।
ଆଉ ୟୁଟ୍ୟୁବରେ ଲେଟରେ ଚାଲୁଛି।
ହଁ ୟୁଟ୍ୟୁବରେ କିଛି
ଅବଭିୟସଲି କିନ୍ତୁ ସାର୍ ସେଠି କହୁଛନ୍ତି ଯୋଉଟା ନା ତାଙ୍କ ଭଏସ ପରେ ହିଁ ଏଠି ଆସୁଛି।
ସରି ଏଇ ଯାହା ହେଲା ଦବାର ଅଛି ଏବେ
ये ଗୋଟେ ଫାକଲ୍ଟି ଆମର ଦବାର ଅଛି ନା।
ଏବେ ନାରେ ସବୁ ଲ୍ୟାବ ଜାମ୍ବୁର ଭଲ ଭଲ ଦବାର ଅଛି ନା। ଥୋଡି ସବୁ ଆସିଛନ୍ତି। ତମେ ମତେ ମୁଁ ଏଇଠି ଅଛି। ମ୍ୟାମ୍ କହିଲେ ତମେ ଆସ ଆମେ ସାଙ୍ଗରେ ଯିବା। ହଁ ଏଠି ବସ। ଏଠି
ନାଇଁ ନା କହ ନାଇଁ ଭାଇ ମୁଁ ହଁ ଆଡମିଟ କରୁଛି।
ଆଚ୍ଛା ଆସୁଛି ସେଗୁଡ଼ା ସେଠି ଦେଇଦେବ ଯେ ନ ଆସିଲେ ତାକୁ ଲେଖିକି ଦେଇଦେବ ଠିକ ଅଛି। ଶିବାନୀ ଆଉ ମୁଁ ଅଛି ଆଉ ଶିବାନୀ ଆଉ ମୁଁ ହଁ ଏତିକି ମିନିଟ୍ ଯାଉ।
मने रखिथिबो आज्ञा हां ए तो चाहा पियो पीसा स्निग्धा
ए मझिरे मझिरे साउंड काई करछि जेति
तो कहारो सार को भी
ना
करछे
ना हां सेठी साउंड करछि क्यों क्यों
हां जो छुआ आछन एडमिट कराओ सार को साउंड होचे इतमे कि मो अंदर कर देछि तांको हां जयपाल वो दिख रहा है रे सर का ही दिख रहा है जो प्रेजेंट कर रहा है उनका दिख रहा है हां रखा है क्या सुनना आज के अपना बड़ा जल्दी यार नया ही हम लेके
टिफिन में ये नहीं
टिफिन खाई
ये नहीं
नहीं जल्दी से ऑफिस को सर खाओ दे हमसे ऐसा
टिफिन टा कौन से ऑफिस लोग को पाई नहीं
ना ना सर भी समस्त दिया मुझे समस्त
ना ना एक
शिवानी जो जो ये ऑफिस रखे सर खाओ दिया मुझे
सीधे तो माने जो सर माने अछन से मुझे दिलानी
और एटा सब
एगुडा को चैम्बर रे जाई तो कोइला अछि रे
डबल डबल लाइन
हां से यार
डबल हो से खाती डबल मैम तो कोई देखी के दियो
हां से तो हम
जाओ देखो केते दिया
भाई एमती नले तो कांगा है जे कॉफी एटा
की कोनी देबे
कॉफी ना
की बोल चाह भी अछि
चाह भी मैं पिएने कॉफी ही पिए जे किंतु इच्छा हो से पूरा बने के दिछन एमती घोली के पूरा
सेठी अछि
तमे तो बढ़िया लागछ तो हो चलो आसिले केता छ ताले ठीक अछि एई भावना भावना रे ए पो जो बिस्किट दिया होछ समस्त को ओके ठीक अछि
ऑफिस रे किसी दिया ही नहीं
ओह दिया ही नहीं गुडा जरीटा नहीं की गले से
30 टा ना टोटल अच्छी के 2 2 4 1 5 से तू बैठी सेमिनार रूम में सब बसछन एक्चुअली
सेमिनार रूम को नहीं की गले बा गुडा जरीटा पूरा सेथरे थिला
जरूरी नहीं करे सेमिनार रूम में सब बसछन
हां ताले सेठ तेबे बोध
के नहीं गले कोन
ए हम स्टूडियो शिवानी आगे नहीं की जरीटा थिले तापर
मना करछन तले आउ कोन नहीं थिबे से टिफिन नहीं नथिबे तले टिफिन ता एति की 30 टा से हाथ रे धरछन एति की गले आउ तो काई 30 टा केतेटा पड़ेओ कैसे नहीं करती
अच्छा एक्स्ट्रा केंद्र रखिया कथा ना खाया पे हम पे भी तो दरकार ना
तो जानेंगे 30 टा से करछन से जाने कि टीचर फैकल्टी से 22 टा स्टाफ सेठी ताको 25 जन हेलेनी से जानी कि सीधा सर अच्छा नक जति ना ना जुदियो न कर हां
केते जाने 89 नहीं हबो हम 1000 टा वाला कर देई छे ठीक बटी हां हां एटा पचरे गसले का को ऐड कर ना ना हां केते ला टोटल 90 ही होचे ना ठीक अछि करू करू 200 भीतर ही करिवे जे अधिक करू करिवे ए शिवानी तुम गोटे जरी पैकेट नहीं की गलो का ऑफिस आड़े
मुझे छाड़ी साड़ी के ऐसे सोचे कहा के मिला कहा के नहीं जोड़ा साड़ी जोड़ा बसचंदी प्रेम सर को भी सेरे मन रखे तो का को देई छ चल अरे गुड सेकंड अपने कुछ नहीं पड़ी गले मुई पा
काजू पैकेट अच्छे से जोटा सेटा ही बेसी टंका एठी के रखी देछि गोटे देख ना जपार
ए रखी देछि हमको से
हम आउ सुनो
We can pose the participants here.
Make full screen. Full screen. Okay. Either. Professor, we will go ahead now.
Kaju packet. Go ahead, sir.
Professor, ready? Professor Adachi?
Yes. Yeah, I'm ready.
You're ready, right?
Anytime
Okay,
is okay.
thank you. Thank you.
Yeah.
Thank you, Professor. Shall we proceed?
Yeah.
It's my pleasure to welcome the first inaugural session. We have now the eminent speaker from Japan, Professor Adachi, QC University. My honor to read his biodata. Professor Adachi, now currently serving as a director, Center for Organic Photonics and Electronics Research, OPRA, QC University. Professor Adachi is a distinguished professor at QC University, and he's also program coordinator of QC University's Advanced Graduate Deep Vinci course on molecular system of devices, and director for the Fukuyama Center for Organic Photonics and Electronic Research. Professor Adachi obtained his doctorate in Master Science, Material Science and Technology in 1991 from QC University, and held position as the Chemical Products R&D Center at Richco, the Department of Functional Polymer Science at Shinshu University, the Department of Electrical Engineering at Princeton University, at Institute of Science and Technology before returning to QC University as a professor. Adachi research combined the area of chemistry, physics, and electronics to advance in the field of organic LEDs, material, and devices from both the materials and device perspective through the design of new molecules with novel properties. The study of processes occurring in individual materials and complete devices, and exploration for new device structures, and he has co-authored over 600 research papers. Recent awards he has received include 24th NAHAB of Organic Chemistry, the Silver Medal, 2019, Memorable Prize 2017, and Thomas Ritten's Research Front Award 2016. He has a name 2018, 19, 20, 21 highly cited researcher in the world. So with this short introduction, it's my privilege to I invite Professor Adachi to give his inaugural keynote address to the audience.
Yes, Professor Shivakuma, thank you for your introduction. It's a great honor to give a talk in this nice webinar. So today I'm going to talk about 3 issues. So I suppose there are many students here. So I put the first topic, the short history from discovery of ETM, stand for electron transport material, to TADF. Actually, the discovery of electron transport material is closely connected to the discovery of TADF. So I'd like to talk about the connection of ETM and TADF. I think this is probably very much informative for the student. And second, I want to talk about cutting-edge technology of hyperfluorescence OLED with advanced materials. And also, finally, if I have time, I'm going to shortly talk about NIR OLEDs. So you know the NIR is also very important wavelengths for the bio and sensing applications. Okay, let's get back to the almost 30 years ago when I was a student, 1985. Actually, I was an undergraduate student. Why I met the interest for the organic electronics? At that time, I got a lecture from Professor Hiroyuki Sasabe. He was in the Riken Institute in Tokyo. Actually, he's my mentor. And I took his classes, and he talked about molecule and polymer organic electronics. and he mentioned that oh, there is no electron transport materials in organic materials. At this time, whole transport material was very a lot of whole transport material has been developed because the OPC applications. OPC is the organic photoconductor, which has been widely used in xerographic, the laser printers. So yeah, there is a very interesting report of molecular electronic devices. The Dr. Forrest Carter, he was in the Naval Research Laboratory. He also published one book and describing the possibility of organic molecular circuit using the organic component. So here you can see the example of the organic circuit. Oh, I was really surprised. Oh, we can make a electronic device.
Professor, slide is not moving, Professor.
Slide?
Yes.
You can make it full screen. You are in the first slide or?
I think second slide.
Oh,
no, you can see.
The slide is not moving. You share the your window, I mean screen.
Or
Not the
something.
PPT.
Okay, I will try again.
Yeah, please.
Okay. So now, can you see this? My second slide.
Yes, Professor.
Maybe it's better to keep.
Make it full screen. Full screen.
Screen is okay.
ये देख यहाँ पे साइड में है.
Can you hear? Can you see my
ये साइड में.
slide?
One thing you can do, that setting also no need to wait for lobby जो एक option रहता है ना.
Full slide we are able to see.
Join directly, no issue.
Okay.
Can you see?
More meeting.
This is my second slide.
हाँ, setting में meeting.
Second slide is shown, Professor.
Oh, something
it's
wrong.
taking time to. Yeah, we are able to see the second slide.
Who can bypass?
Yeah,
the
okay.
lobby?
I'll keep this one, not full screen. Is okay?
People in my organization.
Okay. Yeah. Okay.
Everyone.
So this is the example of molecular electronics reported by Dr. Forrest Carter, Naval Research Laboratory. I was so surprised. Oh, we can make an electronic circuit by using organic materials. Actually, undergraduate student, I was the Department of Physics, not chemistry. But I really suppose, oh, chemistry seems very interesting. So then actually I switched to my subject from physics and chemistry. So graduate school, I belong to the applied chemistry and start the organic electronics. My very first subject was the polyacetylene. So here you can see the photo of polyacetylene. So polyacetylene is completely composed of the CH, no metals. Without metals, you can see a shiny metallic reflection. So this is it's quite surprising. Oh, it shows the metallic, it seems conductive, but actually it shows no conductivity without doping. So I tried to make a N-type doping. So the doping of the sodium is a kind of the donor. So then polyacetylene films became conductive with the electron transport. That was my undergraduate thesis, and at this time, I experienced that the reproducibility of organic electronics characteristics was very, very difficult because the organic materials was very sensitive to moisture and oxygen, and I was so tired to get the reproducibility. So anyhow, so this was my very first motivation why I started organic electronics. So anyhow, Professor Sasabe's word, there is no electron transport materials. That was so important for me because I know that most of the organic devices is composed of P-type and N-type. We need a whole transport and electron transport materials, all electronic devices. So then I entered the graduate school and I tried to find electron transport materials. At this time, one of the very important paper was published by Dr. Chintan in Applied Physics Letter 1986. It's a 2-layer solar cells. CUPC is the p-type, and PTCBI, this is the Pediren derivative. This shows the n-type behavior. So the solar cell characteristics show very good IB characteristics. I suppose, oh, PV is a very nice electron transport material. So I confirm the p-type and n-type by looking at the doping effect of oxygen and even ammonia. In case of the, I'm sorry, the character is too small. PCH2 is a phthalocyanine, free metal phthalocyanine. In case of the free metals phthalocyanine, so this is a conductivity. So conductivity goes up with the doping of oxygen. As the vacuum, the conductivity is quite low, 10 to the minus 14. But once we dope oxygen, oxygen extracts electron, and phthalocyanine became conductive as p-type conductor, and showing the 10 to the minus 8. On the other hand, PTCBI, this showed a completely opposite behavior. So at the highly evacuated condition, the conductivity is high, but once we dope the oxygen, conductivity goes down. So this is the behavior of the N-type. So this indicates PTCDBI, the main carrier is electron, and CPC and the free metal phthalocyanine, the main carrier is holes, plus carriers. So, okay, it's quite interesting. So I suppose, oh, this is p-type and n-type combination. If we apply the positive bias to ITO, CPC, NTCDI, and magnesium, I apply the positive forward bias. And in fact, I observed the electroluminescence from this device. Actually, we reported 1987 annual meeting at Chemical Society of Japan. Okay, and 1988, next year, actually, we constructed the OLED composed of whole transport EML and ETL. It's a double heterostructures. And then, okay, here we reported electroluminescence in organic films with 3-layer structures. So, okay, emitting layer was sandwiched with whole transport TPD and electron transport PTCDI. So, at this time, PTCDI can transport electrons very efficiently. So this is very good, but the problem is the extern confinement, because the PTCDI has a long conjugation, so it's very difficult to confine the extons generated at the EML. So some of the exton is transferred, energy transfer from EML to ETL, resulted in a quenching of extons. So I'm eager to find the wide energy gap electron transport materials. Okay, so 1987 and 1988, it was the very initial stage of the OLED, and before these papers, actually some pioneering reports we can find. So the very first OLED was reported in 1963 using anthracene single crystals. But you can imagine, as far as we use the single crystals, the crystal thickness is the thinnest one is 1 millimeter or 100 micrometer. It's quite thick. In this case, the driving voltage is quite high, more than 100 or sometimes 1,000 volt we require. So researchers try to decrease the thickness of the organic layers, and Dr. Vincent and Dr. Partridge, this paper is very, very nice. So the Vincent reported the vacuum deposited OLED device, and Partridge reported the multi-layer structures, and he also used the very efficient electron injection electrode. And I also want to highlight Professor Hayashi's work Actually, he was my supervisor, and he also reported the double layer structure, which is composed of the P3MT. This is the poly 3 methyl thiophene. It's a electropolymerized thin layer and deposited pyridine. It's a kind of P3MT is a P type. Pyridine is the N type, so it's a PN junction. But again, P3MP has the long conjugation and can't confine extons inside of the pyridine. So, but he observed a slightly enhanced electroluminescence efficiency. So double layer structure seems very promising. So this was 86, and the Chintan's very famous paper, APA, was 1987. Okay, so this is the very initial stage of OLED. Okay, actually, so when I was a graduate student, so I tried to find the electron transport materials with wide energy gap. And actually, I tried more than 100 materials. I synthesized some chemicals, and I found the oxadiazole. So you can see this is the oxadiazole structure, and this shows very good electron transport ability, I found. So by using this material as electron transport layer, we can get the very, very high efficiency electroluminescence. Okay, so here, this is a bilayer, and we use the oxidizer as electron transport layer. As the emitting layer, we use the NSD. NSD is kind of a whole transport emitting layer, and recombination happen at the interface. So exton is well confined at the interface, and we can get the high efficiency. Okay, so then finally, 1990, almost 30 years ago, we could realize the ideal double heterostructure. So double heterostructure, so thin EML was sandwiched between a whole transport and electron transport layer. So NSD was sandwiched between a TAD and a PBD. So this is the thickness dependence of EML, and even at the 50 angstrom, 5 nanometer thickness of EML, we could get the very high efficiency, indicating all charge carriers and exton. It was well confined within a very thin 5 nanometer thick EML. So we could realize the ideal confinement of exton and charge carriers. At that time, I met Professor Steve Forrest at 1991 at the Godo conference. It's a very famous conference, and that was the very first time I met him. And he heard my talk, and he said, "Oh, you could get the double heterostructure." He said, "Congratulations!" I was so happy to get that word. Okay, and so okay, blue emitting device is also always the very important aspect. And 1990, we tried to get the highly efficient blue OLED by using double heterostructure. So actually, so the OLED is the stacked layer. So, and the whole transport is, whole transport mean a molecule is kind of electron donor, electron donating nature, whole transport layer has. On the other hand, electron transport, it's a kind of electron deficient heteroaromatic compound. So it shows a weak electron accepting. So whole transport material has a donating nature, and electron transport material has accepting nature. So we have to stack 2 layers. So at the interface, we have a donor-acceptor interaction. That is the CT and X plexus. So at that time, I mentioned that here. A typical example of X-plex formation can be demonstrated by the combination of E8 and diamine. E8 is this one, oxazole, and the diamine is this one. If we stack this material and this material, we see okay, X-plex formation. The evaporative film of the single E8 layer showed a PL at around 435. However, when E8 and diamine were mixed in a solid state, PL peak shifted to 530 nanometer. So X-plex realized the decrease resulted in a decrease of PLQY and also the redshift. We can get the blue emission if we have an X-plex. So I really hate X-plex. Yeah, but okay. So the alternative idea is the double heterostructure. Okay, between the TAD and the E9, we put the butadiene emitter. So whole transport, EML, and electron transport layer. So three-layer structure, double heterostructure, relax the interfacial interactions, and we can get high efficiency from E3. So then we are very happy to publish the very bright blue OLED using double heterostructure. But interfacial X-plex was the TADF. So in 1990, actually, I have been watching, observing X-plex TADF, but I didn't know TADF, X-plex was a TADF, and the TADF was very useful. So after 22 years later, I found very efficient TADF behaviors. So I'd like to encourage students. So maybe in your daily experiment, you will find many new things. Please don't miss the important finding, like me. Okay, so anyhow, so the, okay, 2012, okay, our, okay, members, Dr. Goshi, and he found very interesting behavior. So, okay, so which PBD, it's electron accepting materials, and MTDATA, this is the donor. So donor always have a shallower homolumo, and accepting PBD has a rather deep homolumo energy levels like this. And if we combine MTDATA and PBD, so two molecules form the X-plex formation, and the X-plex transition is like this. So the transition happen from, if we excite the MTDATA, electron home to LUMO happen, and the electron transfer happen, MT's LUMO to accept PBD's home level, and emissive X-plex formation transition happen from here to here. So X-plex formation, as I said, okay, it showed the red shifted and weak PLQI, but if we carefully look at the, okay, decay, transient decay, we can see not only a prompt emission, but we also see a delayed component. This delayed component is TADF. So here you can see S1 and a T1 over MT and a PBD and X-plex energy levels. In case of the X-plex, S1, T1 energy difference is quite small, so almost 50 millielectron volt. So you know the room temperature energy is 25 or 26 millielectron volt. It's comparable to thermal energy. So because of the such small energy, the electrically generated throughput can upconvert to singlet and contributing to the delayed component. Okay, after 22 years later, we found TDL, but X-plex was the not good because of the containing a non-radiative decays. But basically, we understand, oh, we should provide a donor and acceptors, try to separate homolumo. If we separate homolumo orbitals, we can get a small delta ST. So based on this idea, we design, our group design the tons of DA materials. So around the 2010 to 2012, we synthesized more than 100, maybe I guess 200 new molecules, and one of the very promising materials, 4CZ-IPN and their derivatives. So Dr. Uyama he was computer chemist, and he came to another university, to my laboratory. He has only experience for the organic synthesis, but that was not interesting. So he switched to he came to my laboratory and studied OLED and expand his career, and he designed these molecules. So the advantage of the chemist is that they can synthesize any chemical structures. So physicists can say the design principle. So the discussion between physicists and chemists seems very important. So physics provide the guideline. Oh, we need this kind of homolymer separation. And then once chemists hear just separate homolymer. Okay, we can synthesize wide variety of chemicals. So then, okay, the carbazole is a kind of donor, and the dicyanobenzene is the kind of acceptors. So this is the very compact and highly twisted donor acceptor structures that provide very efficient TADF activities. Okay, so we published in Nature paper 2012, and actually EQE, external quantum efficiency, was 20%. This means internal efficiency is 100%. We could realize. Okay, so once we realized, after 2012, many new TADF material has been appeared, and still it's continued. Okay, so today I want to talk about the design principle of TADF. So basically, so TADF is we have to upconvert triplet into singlet, and so that means we have to flip the spin state. Triplet and singlet has a different spin state. We have to change the spin state. So in this case, everybody suppose, we have to put the heavy metals or halogens, bromide, chloride. But so so these kind of TADF material don't contain heavy metals and even halogens, just the cyano group. So even light element, we can get efficient TADF. So everybody say, it's very much puzzled, but Professor El Said, he's very famous physicist, Mustafa already established how to convert triplet into singlet. He established the El Said rule. I think 1963 or 62. So his formula says K is the rate equation. Rate of risk rate is the proportion to the prefactor A times exponential Boltzmann factor. So Boltzmann factor, if we have a small delta ST, we can increase the K risk. And another important factor is prefactor A. Prefactor A is given this formula. So here you can see a delta ST. So delta ST, smaller delta ST, and make a large A value. So small delta ST is of course important, but also we should take into account this spin orbit coupling factor. So this is the overlap integral between a triplet and a singlet wave function. If we have here. So if we have a very similar wave function between singlet and triplet, in this case, singlet is CT, triplet is CT, same wave function. In this case, spin orbit coupling factor becomes very, very small, nearly zero. On the other hand, if triplet is LE, LE stands for localized excited state, and singlet is CT, different wave function. In this case, we can enhance the spin orbit coupling factors. We can understand if we have a different wave function between singlet and triplet, for example, so not only a CT and LE, but for example, NPI transition. So it's orthogonal wave function that provide a large spin orbit coupling factors. So based on LSAID rule, we can understand how we can promote two-bit into singlet. So today I wanna show you one of the examples. This was well analyzed by Professor Shankar Chen. He's now in the City University of Hong Kong, and he did a very nice work at under the guidance of the Professor Jean-Luc Breda. And okay, so for CZIPM, we like this material very much. It's very ideal structure. Okay, so here, so we have 4 carbazole, 3 carbazole, and 1 carbazole. So bottom 3 carbazole is, you know, the carbazole is a kind of bulky substituent. So 3 carbazole interact each other and actually highly twisted. Maybe 70-degree or 80-degree twisted against the dicyanobenzene. And on the other hand, top carbazole, 2 carbazole is rather okay, freely rotation is allowed. So thermally activated delay fluorescence. So we activate positive type N thermally in this case. So these 2 carbazole can move freely. Okay, so this is quite interesting. So this is the energy gap between S1T1 and S1T2 against the twisting angle of dihedral angle of this angle. Okay, in case of the so here S1 T1 green line. So green line is quite a rather large with increasing the twisting angle. But on the other hand, in case of S1T2 gap, so S1T2 gap becomes smaller, and when the dihedral angle became 145, we virtually, so the delta, the energy gap between S1T2 becomes 0, nearly 0 gap we can get, but not S1T1, S1T2. Okay, and the second point is SOC. So here you can see the 3 different wave functions, S1, T1, and T2s. If you compare 3 wave functions, you can recognize S1 and T1 wave function is very similar. Okay, and on the other hand, T2 wave function is slightly different compared to the S1, T1 wave functions. So because of the similarity of S1, T1 wave function, SOC becomes quite small, 0.06 Kaiser. On the other hand, so T2 and S1 SOC, this one, in this case, SOC becomes 0.51 Kaiser. So almost 10 times higher coupling constant between T1 and S2. Okay, so we can understand. Okay, by twisting the 2 carbazole at the 145 degree, so the virtually the twist energy gap becomes 0, and so T2. Okay, we up convert T1 to T2 summary activated, and then T2 to the S1. We have a very large overlap integral SOC, and if the twisting angle is 145, it becomes 0 gap. So then T2 energy, T2 exciton can up convert to S1. So this is the probable mechanism of TADF in case of the force jet NPN. Okay, so the basically, so the CT singlet CT and the triple CT between these states, the actually spin conversion is prohibited, and the CT triplet into LE triplet is summary of converted, and then spin flipping happen from here to here. So this is the probable mechanism of TADF. Okay, recently the competition of TADF material is so severe. I really enjoy, but it's a very okay, competition is so serious. 2012, we reported very promising this simple It's okay. This very simple. Tetramethyl and BO compound. BO is the acceptor. So molecule is quite small and compact, and actually 4-methyl group induce the very strong donating nature, and actually, okay. So since the molecule is so compact, non-reactive decay is well suppressed, and we really surprised that the delayed component, the lifetime was the 750 nanosecond. Always the up conversion speed was longer than 1 microsecond, but at that time, this was the very first report showing the very quick up conversion from two-bit into single. We are very much excited, and so in this case, K yes, K risk is 1.9 times 10 to the 6. And Professor Yasuda, he introduced very unique molecules. His idea is the introduction of sulfur. Sulfur is a kind of, slightly heavy metal, heavy atom, and that enhance the spin SOC value. So in fact, the K risk became 3.5 times 10 to the 6. And Professor Aizawa combined both tetramethyl this unit and the sulfur unit, and surprisingly, he reported last year in Science Advances that the risk rate was almost 10 to the 8. Very high risk rate he reported. Also, the Professor Kaji reported the kind of intramolecular express system, and he showed the risk rate is almost 10 to the 7th. So very unique molecule has been reported recent years. In fact, the short lifetime is quite important. Yes, quite important because almost the OLED degradation happen at triplet states. Okay, so here you can see a Jablonski diagram. We have a singlet and triplet, and triplet extron has rather longer lifetime, microsecond or even millisecond order. And then we upconvert because of the longer lifetime nature. Triplet extron experience the triplet annihilation or triplet polaron annihilation happen that induce the hot extons. So hot extron has the energy higher than a 5 electron volt. It's very dangerous because the chemical bond, for example, CN bond is a 3.5 electron volt. It's higher than CN bond. So such hot extron initiate the degradation of organic molecules. So we should quickly deactivate triplet by upconverting or deactivate to the ground stage. But of course, to get the high efficiency, we don't want to lose non-radiatively. So we should quickly upconvert triplet into singlet that contribute for the good device lifetime. Actually, in a group, try to systematically synthesize the robust TLF materials. This is one of the examples. So 5-CZBN. So here, this is another TLF materials, which was firstly reported by Diwan in Tsinghua University in China. He introduced 5 carbazole and one cyan group. This is compact molecule again. And we introduced actually small modification. Small modification helps very much. So methyl groups, phenyl group substitution, and like this. And actually, we succeeded make a quick up conversion by expanding pi conjugation, methyl group and phenyl groups. So here you can see CT1 and CT triplet and LE states. So LE state goes down by expanding the pi conjugation because the LE state localized at the carbazole unit. So by expanding the carbazole pi conjugation, we can decrease the LE states methyl group and phenyl group like this. So by introduction of the phenyl group, in fact, the risk rate became almost 7.2 times 10 to the fifth. So that means almost 3.5 times longer, shorter, higher risk rate we could get. So small modification helps to enhance the risk rate. And fortunately, we found a significant increase of the device lifetime. So unsubstituted materials. So we started the OLED with the initial luminance of 1,000 candela per square meter. And within 35 hours, we almost lost 10% luminance. But on the other hand, by phenyl substitution, even at 100 hours, we can still keep the LT97. So just 3% loss, even at the 100 hours continuous operation. Okay, so the chemical modification is quite important to get a longer device lifetime. So I don't want to talk about the detail of degradation mechanism, but I just want to show the mechanisms. Okay, so this is the cross section of device architectures. So electron blocking layer and emitting layers here and hole blocking layer. So initially, at the fresh sample, recombination mainly happened at the middle of the emitting layer. But after degradation, because of the degradation of the emitting layer, electron transportability decrease, and then recombination site shift to the close to the hole blocking layer. So, and then some of the hole is injected into the HBl. We don't like, but in reality it's happened. So then some of the recombination happen at the EBL that also induce the degradation. So anyhow, so the TLF molecules degradation decrease the electron transportability and resulted in unbalanced hole and electron recombination. That is the reason of degradation. Okay, rest of the time I want to talk about the recent cutting-edge technology of hyperfluorescence system and also the NIR. I just want to talk about the point. Okay, so the TADF. So here you can see HDT1. This is our most advanced TADF materials. In the bottom, carbazole was substituted by a tar-phenyl group. And also some of the carbazole, 2-carbazole was substituted by phenyl groups. This TLF material showed a slightly blue shift 486 nanometer, and the risk rate was almost 10 to the 6. Very nice material, which was designed by Dr. Chan. And but TLF has a fundamental problem that is the actually the spectral width. You know, the most of the CT molecules show the broad emission spectrum and not good for the ideal emitter. So then our idea is basically we generate exciton at the TADF and transfer the energy to the terminal emitter. So we co-deposit not only host materials, TADF and terminal emitter. And the terminal emitter concentration is 0.5. Very, very diluted conditions because we want to escape direct carrier exciton generation at terminal emitters. We forced to generate exciton at the TADF assisted dopant and transfer the energy to terminal emitters. So this works very well. And actually, so here, this is the comparison of left one is the fluorescence device and the right one is the hyperfluorescence device. Of course, hyperfluorescence provide almost 4 times brighter luminescence like this. And this is the comparison of fluorescence, phosphorescence, TLF, and hyperfluorescence. And hyperfluorescence satisfy all requirements as the display applications. So because of the time limitation, I don't want to talk about the details, but okay. Okay, I should quickly talk about two issues. One is the FLET. So black line is the emission spectrum of TADF assisted dopant. You can see, oh, it's very broad. Almost full width at half maximum is the almost more than 100 nanometer. It's very, very broad. And we, okay, transfer energy to these materials. And this solid three line is the absorption of terminal emitters. So here you can see a hatched area. This is the spectrum overlap. Between this emission and absorption spectral overlap, we transfer the energy by FLET. And in fact, the composite film only show the emission from these terminal emitters. So PLQR is quite good, close to 100%, and FWHM is also around the 30 nanometer. It's good for the display applications. Even with these not perfect overlap, but we can nearly 100% energy transfer to the terminal emitters. And this is the OLED behavior. So AQE showed close to the 20%, and the wavelength was the best one is 471, and the LT90 lifetime as the best one is close to the 40 hours continuous operations. So hyperfluorescence seems quite promising. Okay, I finally quickly talk about the NIR OLED. So NIR is also the very strong demand for the bio and also the sensing applications. Actually, many, not only Japanese companies, but many cell phone company also asked me to develop the NIR OLED. So NIR has a lot of application for biosensing because they have a window. For the bio, we have a first window and a second window. Second window is too much wavelengths and it's very difficult for the organics, but the first window around the 900 or 940 is possible for the organic emitters. And also the advantage of NIR OLED is we have a possibility with the fusion of OLED. Not only RGB emitters, we can also put the NIR pixel inside of the OLED pixels. So we have a very nice compatibility with the OLED technologies and ease of micro fabrication. So you know the micro LED is also the competitor, but it's quite surprising. Micro LEDs EQ is not so high, 10% to the goes down 5%. So in case of the 10 micrometer, so the EQ is just 5%. Oh, OLED can realize the 20 or 30 or 40%, but the micro LED is just 5%. Oh, it's a good news. Okay. Okay, and then here, just summarize the present status of the NIR OLED, and you can see the best one is close to 10%. Of course, it goes down because the energy gap load. The organics unfortunately decrease the PLQY follow the energy gap load. But anyhow, still EQE is 0.1 or something. So we actually optimize our material systems, and this is the host materials, and this is the TLF materials, and this is the emitters. So we co-deposit three materials. I don't talk the detail of the energy diagram, but it provides a very ideal NIR emissions. Okay, this is the fundamental behavior of our NIR OLED. Wavelength is the 940. EQ is 1.5%. Thermal stability is quite good. LT95, 1 ampere is 100 hours. Actually, if the current density is 100 milliampere, even a 500 milliampere per centimeter, almost no degradation was observed. It's very promising. So I wish this technology can be commercialized in the future. Okay, I'd like to show you the latest achievement of RGB emission realized by our startup company Qlux. And so here you can see red and green is ready for the commercial use, but still blue is we need maybe 5 times or 10 times improvement for the blue. Also, the Qlux reported the very much advanced green hyperfluorescence system. So the phosphorescence is here and hyperfluorescence here. The ultimate is here. So close to the hyperfluorescence satisfy close to the BT requirement for the BT 2020. Yeah, it's a good news. Okay, finally, I'd like to summarize the progress of the organic emitters used for the OLED. So long time fluorescence material has been developed more than 50 years, and second generation phosphorescence was appeared. And of course, this is amazing technologies. And the third generation, so it's a rapid, last 10 years, very rapid material innovation was happened, and hyperfluorescence. Also today I didn't mention the MR multi-resonance emitters, but that is also promising. So I don't know, next generation is the logical or QD or perovskite, but all these emitter has the possibility to get the 100% quantum efficiency. I wish young generation will pioneer the new technologies. Okay, finally, I'd like to thanks to the all our members, and also special thanks to the funding agencies, JST and Qlux, for their financial support. Okay, thank you very much for your attention. Yes.
Thank you, Professor. Maybe we can have one or two quick questions if anybody having.
Hello, may I ask?
Yeah, please go
Yeah,
ahead.
this is hello, Professor. Good afternoon. This is Rajamalli.
Oh, Raja. Nice to see you. Yeah.
So actually, I have one small curiosity question. What is the advantages of fabricating NIR pixels in the display product?
Actually, if we combine the NIR emitter inside of the OLED, so it's also provide a sensing light source. And actually, I don't know the detail of the application, but many companies ask me to realize, and they want to combine NIR pixel into the OLED panels, and they seems to use for the light source for the detection of many objectives, and yeah, actually I don't know, but
yeah, I think Professor Rajamalli, this NIR LEDs people are using for food security. You can, the functional group analysis, like just directly you can get the information about what the composition of your food product is, and then imaging, etc. Like it's a one rapid advancement. Of course, the inorganic LEDs have already been, have reached some height, but organic need to go. I think chromium-based phosphor LEDs are already, booming. So because of course organic LEDs may be the futuristic thing.
Okay. Thank you, Professor, for very nice talk. Thank you, Professor.
Yeah, it will be a pleasure to see you again. Yeah.
Hello, Professor. Good morning. Sir, I have one question.
Yes.
Sir, you shown in one of your slides that putting phenyl ring on the carbazole is reducing the delta AST.
Could you say again? Could you please say again?
Sir, putting phenyl ring at the para position of the carbazole is reducing the delta AST value. In fourth is an IPN type of molecule.
So I'm sorry, could you please say again? I couldn't catch your voice clearly.
Sir, in one of your slide, you shown that putting phenyl group at carbazole position,
Yes.
reducing the delta ST.
Reducing delta ST.
Professor, you in the beginning of your slide, one of them is modified this blue emitter with the putting carbazole, phenyl, etc.
Yes.
Like in the donor site.
Yes.
So what is the advantage of having phenyl functional agent in the carbazole moiety? Whether it can reduce the delta EST is asking.
No,
Phenyl,
sir, told that it is
phenyl
reducing delta ST, but
if
what will be the impact on the emission color? Whether it will red shift or it will blue shift?
Yes. Actually, if we substitute the carbazole with the okay, yeah. Maybe I can share this slide. Actually, it induced the slight. Can you? Yeah. Can you see the? Yeah, this spectrum. Yes. Unsubstituted one is red one, and you can see a phenyl substitution slightly induced red shift, but still not so large one. But but anyhow, it's not a good idea to induce the red shift. So then we decided instead of the bottom carbazole, we introduced the terphenyl. So terphenyl group induce the blue shift. That is good for the blue emissions. And I should also say, I'm sorry, I didn't have a time. I didn't mention that. But this is the phosphorescence spectra of phenylcarbazole or dimer, trimer, pentamer, and surprisingly, so the phosphorescence spectrum doesn't change. You can see the onset is exactly same, independent of the chemical structures. So that means LE state completely localized at one carbazole. Yeah, it's good news. But anyhow, so if we expand, pi conjugation of the carbazole. So here you can see two-bit energy level is also slightly red shifted. So methyl group and phenyl group, so almost 0.2 electron volt red shifted with the phenyl carbazoles. So maybe I think para position is not a good idea. Maybe you can substitute meta or another position that suppress the significant red shift.
Thank you, sir.
Thank you. Nice. Yeah, thank you very much for a nice
Thank
question.
you, Professor. Now we thank you very much for sparing your time, and please join the audience to thank Professor Adachi.
Yeah, thank you. Thank you very much.
Thank you, Professor.
Thank you.
Yeah, he's a Professor Justin Thomas is a convener. Yeah, Professor Justin. Unmute yourself.
Yeah, thank you, Professor.
I think the second paper, Professor Raymond Wong, joined. Welcome, Professor.
Hi, hello.
Yeah, Professor.
Can you hear?
Yes, Professor. We are hearing you.
Can you see the slide?
Yeah. So now we have the second talk for Professor Raymond Wong from Hong Kong University. Now I request Professor Justin Thomas to introduce Professor Raymond Wong.
Thank you, Professor Siva Kumar, giving me an opportunity to introduce the next speaker of the session. It's my pleasure to introduce to the audience Professor Wei-Yuan Wong, commonly called as Raymond. He is a well-known figure in organic electronics, and most of the audience here may be well aware of his work in organic electronics. And it is my also pleasure to say that one of my doctoral student, Dr. Podarla Babu, is currently working with Professor Wong as a postdoctoral fellow. And Professor Wong is Dean of Faculty of Applied Science and Technology Textiles and also a Claria Gold Professor in Energy, Chair Professor of Chemical Technology, Department of Applied Biology and Chemical Technology. He is also a president of Hong Kong Chemical Society, associate editor of the prestigious Journal of Material Chemistry C, and editor of Journal of Organometallic Chemistry published by Elsevier, and also editor of topics in current chemistry. And he has fetched numerous number of awards. I'm not going to list all of them, and it itself will take more than 20-30 minutes. And I don't want to be stand in between the audience and Professor Wong. With this brief introduction, I would like to welcome Professor Wong to share his knowledge on the recent advances in phosphorus and melt complexes. Welcome, Professor Wong.
Okay, thank you, Chairman. Can you hear me?
Yeah, we are able to hear you. Please go ahead.
Okay, thank you. So it's my quick pleasure, to give a talk, in this webinar. And today I'm going to share with you our work on some phosphorescent metal complexes, which can be useful for OLED as well as other optoelectronic applications. So as we know, phosphorescent metal complexes possess many advantages, including the good photostability, long emission lifetime, high quantum yield, large stroke shift, as well as tunable emission wavelength of the materials. Actually, we are most focused on the use of platinum as well as iridium complexes in our research. And as I pointed out before, one of the important applications is on organic LEDs. And Professor Adachi also just mentioned a number of works on this topic, using his very nice materials. And for metal complex, they can also be useful for chemical sensing as well as bioimaging. And today I will also share with you some of our work on the stimuli responsive material of using this type of materials. Actually, our work date back some years ago, in developing some multifunctional complexes which are useful for OLED applications. For example, if you try to improve the hole or electron transporting properties of the complexes, we can introduce some functional groups like triphenylamine, fluorine, or carbazole as the whole transporter. And for those with electron deficient chromophore like the sulfone, boron substituent, sulfoxide, phosphine oxide, they are very good electron transporting or electron injection materials. So we can actually functionalize this ligand in different platforms for the metal complexes, including the homoleptic and heteroleptic iridium complex, as well as the platinum complexes. So from our previous work, we found that the use of carbazole like this, can lead to a very robust and highly efficient OLED materials. And it is also interesting to see that the use of different substituents on the pyridine group will lead to very efficient color tuning of the complexes. As you can see here, we can easily tune the color from blue-green to saturated red by adding some substituents on the pyridine ring. For example, if you are using some electron withdrawing groups, it will redshift the color from green to orange. And these complexes are all sublimable under vacuum, so we can easily fabricate highly efficient OLED devices. And then we also try to use some so-called main group elements in the development of some very efficient emitters. In fact, some other research groups have also used these main group elements in developing the host for phosphorescent OLEDs. So actually, we have summarized the work, in this review, talking about the functionalization of these hosts as well as emitting materials by using the main group elements. So one of the most interesting work, in this area by us, in the past, involved the use some group 13 to group 16 elements, including the boron, nitrogen, oxygen, silicon, phosphorus, sulfur, and their derivatives. And this slide summarizes the work, that we have carried out. So we find that the use of different main group elements on the PPY chromophore can lead to a substantial change in the emission color. And we believe that the color tuning is actually caused by the shifting the charge transfer character from the original pyridine ring to the electron withdrawing groups, okay, attached to the PPY. Okay, for example, for boron, the electron withdrawing boron group actually will push, we will withdraw, okay, electron from the pyridine ring, so that in the LUMO level, okay, the electron will be more localized on the boron instead on the pyridine ring. And such color tuning strategy can also be applied to the platinum complexes, as you can see from here. So we can have a very beautiful color tuning picture for these platinum complexes. And it is even more interesting to see that for this platinum complex, because of the possible aggregation effect, we can fabricate a very simple white light OLEDs. Okay, for example, for these two compounds, in solution or in the solid state, normally they appear to be green light emitting. But when we fabricate the device in such structures, we observe actually a white light emission. And actually the green emission is still here in the spectrum. And the blue light here is due to the inefficient energy transfer from the host to the gas. So we can still observe the blue emission here. And because of the square planar geometry of the platinum complex, we can also observe low energy eczema, okay, due to the interaction between the platinum complex in the solid state. So we can see three major peaks in the emission spectrum, which actually scan from about 400 to 700 nanometer. So it covers a very broad range. So that's why we can observe a white light emission here. And for this very simple device, okay, we can get a very high color purity as indicated by the color entering index. So for our device here, it can reach up to 97, which is even higher than the OLED, okay, than the sunlight, okay, under the experimental setting, which is normally about 90 only. And the color purity is actually depends on the CLI. The higher the CLI, the better will be the color purity. So this can be a very simple system to get a very pure white light for illumination. So we believe that this approach can be useful for deprecating the sunlight, okay, for illumination. And as you can see from this cartoon, we are trying to simulate the white light spectrum with the sun, which can produce very good color for the objects that we would like to observe. And this is the practical situation. When we are trying to say about the color purity of the white light, we have to make sure that we can reproduce the color of the objects. So inside a dark room, we have put 4 pans, okay, of 4 different colors. And if the white light here is pure enough or white enough, you should be able to see the 4 colors very clearly. And this is the situation for the daylight. So as you can see, basically we can get very clear 4 colors from this white light. So it shows a very excellent or outstanding color reproduction based on this illumination source. And these are some previous work, okay, in the past few years. And more recently, we are also trying to develop a very efficient full OLED or even the NIR emitters for other applications. And as we know, basically, many of the iridium blue emitters are rather unstable. And so we are trying to make use of the very strong iridium carbon bond in the carbene complex, okay, because of the very strong ligand field of the carbene compared to the traditional N heterocycle. And we have made a series of iridium carbene, as you can see from this slide. And actually, we can get a quite reasonable performance, okay, for this material, okay, in the devices. And further, we would like to explore, okay, whether we can establish a very useful color tuning strategies to again get emission of different color. And traditionally, we have the RGB emitters. Okay, these are some commercial benchmark materials. And for the NIR emitters, and usually they consist of very conjugate and largely extend ligands, which can allow the emission in the very low energy region. And most of these compounds are rather complicated, to synthesize, as well as very poor solubility. So we need a new method to develop a very simple NIR emitters, which are more soluble, and they are more easy to synthesize. Of course, we need very good performance as well for the NIR emitters. In many cases, the NIR emitters are not very not very highly efficient, because of the energy gap law. So our strategy here is to make use of some substituents, on some functional group, and also to change the conjugation effect. And you can see from this slide, we have developed a very nice color picture for blue to near infrared materials. For the carbene, as I mentioned before, we make use of this iridium carbon bond to raise the LUMO level, so we can actually increase the energy band gap. And then we can make use of other electronic withdrawing substituents, including the CF3 and also the fluoride group on different aromatic ring to tune the emission color. And we also try to change the number of these substituents, which will also play some important role. And finally, you can see from the last compound here, as I pointed out before, usually we need a very extensively conjugated structure to get NIR emission. But in this case, we just need to make use of this conjugation effect, as well as the electron withdrawing purity ring, which can actually decrease the band gap substantially. So for this compound, it will actually lead to a very low energy emission in the NIR region. So basically, we can get a couple of emitters with different colors by changing the conjugation effect as well as the number of substituents. And these are just the synthesis of how we can make it. And as I would like to point out the NIR emitters, the synthesis are rather simple, and also the solubility is very good. So this is one of the beauty of this system. So you can see the emission spectrum, scanning from blue to NIR, up to about 730 nanometer. And the experimental data for the emission are also consistent with the DFT calculations of the compounds. Of course, the band gap will have some difference, but the trend is the same. For the iridium-6, then basically the band gap is the smallest among the series of compounds. And by using this compound, we can make both the monochromatic as well as the white light OLEDs, using different structures. For the emitters, we can use this structure for the monochromatic OLEDs. And then for the blue as well as the green and the red color, we can make a 3-color system, blue, green, red, to make the white light OLEDs. And these are the actual device pictures, for the 3 primary colors. And the efficiency are also quite decent, for these materials in the device. And I would like to highlight the result for the NIR case. You can see the EQE can reach up to 4%, which is quite rare in the literature. And even we can get a very good performance up to 44.5 EQE. The structures are more complicated and hard to make. And for the highly conjugated one, actually the performance are also not very attractive, in the literature. So this simple approach can be a very good way to design, future NIR emitters. Another recent approach that we have adopted is to use a cyano group, okay, in this type of materials. And as you probably know, okay, this isoquinoline compound is a very a successful story, okay, for the red emission. But how can we try to redshift, okay, the emission to the NIR region? And we have introduced a very simple way, okay, by acting the electron with joint cyano group at this position on the isoquinoline. And if we can also change the benzene ring to the phenol ring here, we can even further redshift the emission really down to the NIR regions. Okay, for this compound, we can get a very deep red, okay, but still the peak is in below 700. But if you can change the phenol to the phenol ring, then the maximum here will go beyond 700 nanometer. And this approach, again, provides a very simple way to make some NIR emitters for the iridium complexes. And also the structure is very simple and very soluble. Okay, so this is the synthesis, okay. So for the NIR emission, okay, emitter, actually we just need a 3-step, okay, for the synthesis, and which is much more convenient than the traditional way reported in the literature. And for the device performance, they are quite attractive, okay. So the for the red one, we can get up to 10%, and even for the NIR one, it is close to 10%. So they are very good, okay, to in terms of the performance. And these are the stability tests, okay. So after some cycles, the operational lifetime remains reasonable, although not very attractive, but there are actually very rare reports for the NIR emitters in terms of the device performance in the literature. So this can serve as a very good reference how stable the materials can be. Okay. And we also try to add other substituents to the other aromatic unit, okay, for this type of materials. And we find that comparing with this tertiary butyl one, if you change it to electron with joint group, there will be a slight blue shift. But if you change this T-butyl to 2 methyl group like this, then you will again need to red shift. So we can also control the color of the emission by changing the substituents on the other aromatic rings. And this is another useful methodology that we can use to tune the color of this low energy emission material. And actually the device performance are also quite decent, okay, in these cases. And the efficiency can reach up to 7%, which is quite good, okay, for iridium complex also. Another interesting story here is the use of the so-called piling group, okay, to control the excited state energy of this iridium complex. As you can see from the literature, usually the color will be determined by the cyclomethylated ligands in the iridium ECAC complex like this. So if you change the cyclomethylated ligand from here to the isoquinoline one, then the emission color will change from blue to red very easily. Okay, regardless of the auxiliary ligand here. But if you change the auxiliary ligand, okay, from ACAC to the dipyrene group, okay, we find that the cyclomethylated ligands no longer has a very strong influence on the emission color, okay, because the energy level are actually dictated by the dipyrene auxiliary ligands instead. So from our work here, we can see it shows a very strong resistance to the color change. Okay, if you use this dipyrene ligand. So in the traditional case, if you change the cyclomethylated ligands, okay, with the auxiliary ACAC, then the emission will follow, okay, a barochromic effect. But if you switch this ACAC by this dipyrene, then the emission will be mostly, okay, red in color. So it shows a very strong resistance to the barochromic shift. So this is consistent with our prediction and also experimental data. So as I point out, okay, the change of CN ligands can influence the emission wavelength of the ACAC complex. But for the dipyrene complex, the change of this CN ligand can hardly change the emission color. Okay. Actually, the dipyrene ligand, okay, will have a very strong influence on the LUMO levels. Okay, but for the other case, it is the CN ligand that will dictate the LUMO levels. For this device, the efficiency are not very great, okay, but still they are not too bad, okay. But still, we need to find other ways to control or to improve the performance in the future.
कटलेट 10 रुपए, सैंडविच 40 और वो जो मिल्क कटलेट था मतलब वो
And from the literature, we know that more recently, people are interested in making some so-called broadband emission, which are useful for two-color white light OLED systems. Okay, for two-color, okay, normally we have to use a blue and yellow or orange emission. Okay, but in order to have a better coverage in the visible region, then if we have a much broader emission, then it will be much better to improve the CLI. So in the literature, there are many reports on the yellow emitters, but usually the emission wave bandwidth, okay, is not very broad. Okay, and usually for many of these compounds, they have involved the use of chlorine, fluorine in the compound. Okay, and for this CF bond, usually it is very unstable. So in our work here, we would like to develop some broadband emission by using this so-called chlorine substituents. Chlorine has different electronegativity from fluorine. Okay? Actually, it's less electronegative, and it will make the Cl bond stronger. And so we expect this compound will have a better stability than the fluorine case. And actually, these ligands were developed, okay, by us here, and this compound can lead to a very broadband yellow emission, which are useful for two-color white light OLEDs. As you can see here, the synthesis, okay, step for this compound, and we can also change the oxyligands, okay. And these are the photophysical data. And most importantly, you can see the full wave at half maximum can be over 100 nanometer, which is very important, okay, for our work here. And the quantum efficiency, okay, in solution are also very high for many of these compounds. So for the yellow OLED, okay, you can see for the EL spectrum, the bandwidth is also quite decent. And the EQE and also other performance parameters are very good, okay, for these devices. And the full wave at half maximum is quite close to the PL case. And okay, we can try to fabricate the two-color white OLED, okay, by using these materials. We can get a very decent two-color spectrum. And the performance, okay, efficiency are also quite reasonable. And we would also like to use these ligands, okay, to make some so-called subprimable ionic complexes. And take back some years ago, okay, we have reported the first example of using ionic iridium complex for evaporated device. Okay, but at that time we use just a very small anion, okay, so that the sublimation ability of our compound is not very good. And later on, Professor Donnan, okay, in Tsinghua University, he has studied extensively the use of different counter ions, okay, to control the sublimation ability. Okay, so based on that, okay, we have developed a new set of ionic complex with this bulky counter anion. And these counter anions can improve the stability, okay, to a sublimation of our materials here. At the same time, okay, these yellow emitters can show very broad emission bandwidth. As you can see from the PL spectrum, the full wave at half maximum can reach up to 100 nanometer, which is very impressive actually. And the solution quantum yield are also very high, up to 0.9, because of the presence of this bulky counter ion. And in view of this result, we can fabricate the device, okay, later on by using this emitter. And we can also check the case in the thin film as compared to the solution. And you can also see a very broad bandwidth, okay, for these compounds. For the device, again, the bandwidth for the EL, okay, is also very broad. And the efficiency are also very attractive, okay, for such type of for these ionic base iridium complexes. And the use of this yellow emitter in white OLED, okay, can be established with a very reasonable color purity, and the CIE coordinate are also quite good, okay. So by using different ligands, okay, especially with this CCl bond, we can fabricate broad emission bandwidth, okay, for the devices. So far, we have discussed some iridium or platinum complex based on mononuclear framework. And we also try to explore whether we can increase the nuclearity from one metal to two metal center. Okay, we have a very interesting piece of work here by using this ligand as a bridging ligand, okay, to link up two iridium together, so that we can get a bimetallic, okay, complexes. But because of the nature of this ligand, we can actually get a set of isomers. In fact, we have a pair of enantiomers, okay, which are mirror image, and then we also have a mesoform with a perpendicular mirror plane here. And for the racemic mixture, it's very difficult to separate them by normal chromatography. But for the mesoform, we can separate them. Okay. So in the following study, basically this enantiomer exists as a mixture. Okay, but for the mesoform, they can be isolated, okay, in a pure form. And another interesting work, okay, from here is that we find that by comparing the emission with the monomer, which is a model compound, we see that the emission wavelength as well as the device performance can be controlled by increasing the nuclearity, okay, from one metal to the two metal center. And these are the structures, okay, for one of the enantiomer and also the mesoform. And this is the PL spectrum, okay. For the monomer, okay, you have a green emission, and for the dimer, then you have basically a red or orange-red emission. And by looking at the DFT calculations together with the experimental data, we found that by increasing the nuclearity, we have actually lift up the HOMO and lower down the LUMO. So we can have a much narrower band gap, which is consistent with the redshift of the emission from green to red. For the device performance, okay, using this dimer and monomer, you can see the EL spectrum, okay, again a redshift in the emission, suggesting that the excited state is the same in both EL and PL spectrum. And by increasing the nuclearity, we can see that the device, okay, using monomer in C can be increased to the device using the dimer. So, for example, the efficiency can be increased almost by 2 times, okay, in this case. So this is another strategy we can use to tune the color and also the performance of the OLEDs using a very similar ligands. Okay, so this is the performance parameters, okay, for these devices. And we would also like to explore the use of this yellow or orange emitters in the solution process by like so-called single layer pellets. And for solution process device, it is good for large area applications. And also the cost of consumption is usually lower than that for the evaporation method. But for solution base, okay, white light pellet, the bottleneck problem is the low efficiency, okay, which is very harmful for practical applications. And we have tried to study this area, okay, date back to 2009, okay, where when we first published the paper in using the solution processing method for single emissive layer white light pellet. And at that time, the efficiency is actually quite low, okay? The power efficiency is only up to 20. And then 2 years later, we have boosted up the efficiency up to about 37. But it is still below the threshold for the fluorescent lamp, okay, which is usually in this range. So we never gave up, okay, so we have developed another orange emitter, okay, and we have another world record of about 47 lumens per watt for the performance. So actually a few years ago, okay, we have published another paper, okay, in iScience, and we have again used this compound to improve the performance. So this is the work, okay, that I would like to tell you here. So in this work, instead of the commercially available Furpack, we have developed, okay, together with my collaborators in Changchun, a very efficient Bull emitter. We also compare the effect of the substitution position on the performance of these two Bull emitters. Okay, one is meta position and the other is para position. And we found that the one with para position gives a much better performance. And this Bull emitter, okay, also show a very high cheaper energy level. So for the performance parameter, okay, for our new Bull emitter and the benchmark, okay, Furpack, you can see that the emission actually is more bullshift, okay, compared to the Furpack. And the quantum yield and also the cheaper energy level are more desirable than the Furpack one, okay. And we also make use of this very good dendritic host, okay, in combination with this Furpack, in combination with this Bull emitter. And because of that, okay, it shows a much better performance for the Bull emission. And then when it is combined with our orange emitter, then it can give a very good performance. As you can see here, the maximum power efficiency can reach up to 96 lumens per watt with a light out coupler. So this is our latest work. So this solution processing method can be as good as the evaporated method, okay, evaporation method. And it also provides a very comparable performance as compared to the fluorescent tube used in our daily life. But of course, future work needs to be done to improve the stability of the devices, okay, which is very essential for practical applications. Okay, so this table summarizes some of our work, okay, in this area. So the maximum, okay, even can reach up to this value. But at 1,000 luminance, okay, then the maximum power efficiency is 68, okay, without the light out coupler. But if we use the light out coupling technique, then we can reach up to 96. And then I would like to spend some time, okay, to talk about the phosphorescent soft salts based on two oppositely charged metal complexes, which are under development, okay, in the recent years. And for soft salt, by definition, okay, we have one ionic complex and one anionic complex, which are usually held up by strong electrostatic attraction and van der Waals forces. In some cases, okay, we can also have pi-pi stacking interactions. And this soft salt can be useful in different areas of material science, okay, especially in bioimaging and also stimuli responsive materials. So first of all, I would like to show how it can be useful for NLI detection, okay, and imaging piece of work. So some years ago, okay, we have developed this soft salt with these two different ligands. For the red emitting material, we have a Dankering pyridyl ring at the VN, so that it is very sensitive to the pH value. But for the other one, it is a blue emitting anion, which is not sensitive to pH. So if you have energy transfer from blue to red, then you will see mostly the red emission here. But if you actually quench the blue emission, then you will see the main emission to be red in the region. Okay, so we have the compound A1 for the red, okay, and then the C1 for the red, okay, A1 for the blue. Then we can make a soft salt with the two ions together. And we found that this soft salt can be a very useful probe for pH detection. So first of all, if you look at the emission spectrum, okay, so this is the blue and this is the red. But if you change the concentration of the soft salt, okay, so if you increase the concentration, actually you are quenching the blue emission. You get a stronger red emission color. Okay, this is also consistent with the titration experiment here. Okay, if you have a high concentration for C1, then you have a stronger emission at the red color region. And this system is very sensitive to the pH. Okay, if you change the pH down to 2, okay, so it is very acidic with a high concentration of hydrogen ions, then you will actually protonate this pyridine, so you will not be able to see the red emission. So you will only get a blue emission color from the anion. But if you increase the pH, okay, up to 8, then the red emission will come back because the protonation is hindered. And you can see from this diagram, by changing the pH, then the intensity of the blue emission change a lot. And for the co-staining experiment, okay, using a mixture of this and also the pure soft salts, and you can see the overlapping area, okay, are somehow different. So this shows that the S1 actually remains intact in the co-staining experiment. And one of the advantage of using this soft salt, okay, in the imaging is based on the radiometric ratio of two emission which are very separate in the wavelength. Okay, one is red and one is blue. So if you look at the blue channel, okay, by changing the pH, the contrast is not so high. Okay, even for just for the red color, not so good. But if you have the radiometric ratio image, then the change will be very significant. So it can be useful to image, okay, the reagent in the cell using a ratio of two emission intensity. And we can use the lifetime imaging to probe, okay, this change as well. So if you look at the average lifetime of this soft salt, by lowering down the pH value, you can see the intensity will actually increase. So this is very useful in lifetime imaging, okay, using radiometric probe. And this also follow a linear relationship, okay, in the calibration curve, okay, under different conditions. So after you set up this calibration curve, you can measure the intensity to see, to detect, okay, the pH value of a certain medium. So it is a very useful way to determine the intracellular pH fluctuations, okay, using this soft salts.
मैं करने जा रहा था, म्यूट ऑल करने जा रहा था.
And then we also develop a very interesting probe for in vivo imaging. Normally for biological study, people like to use the low energy light source, such as the NIR emitter. Okay, so in this case, we have developed NIR emitting soft salts. Okay, as you can see from the crystal structures, we have very close interactions between the platinum and also the pi aromatic interactions. And the emission, the NIR emission is believed to be due to the metal to metal charge transfer, metal to ligand charge transfer. Okay, which is has been well developed in the literature. And these are the photophysical data, okay, of our monomer and also the soft salts. Okay, and our soft salt actually can behave quite well, okay, in the performance as well. And the emission bandwidth, okay, is actually in the near infrared window. And soft salt show very good photo stability, as you can see from this diagram, and very low cytotoxicity from the MTT studies. So they can be useful in vivo studies. And you can see here in the buffer, original buffer without the dye, there's no emission. But with our dye here, then it shows a very bright NIR emissions. So when we inject the compound in the buffer into the mouse, then you can detect the intensity of the emission from different parts of the region of the body. So this is very useful in our study, okay, without causing much damage to the animal. So lastly, I would like to introduce to you a very recent piece of work on using this soft salt in the on-demand regulation of the excitation wavelength dependent emission. And recently, people are excited, okay, in using the excitation wavelength dependent emissions because of the very versatile and non-damaging, okay, nature of this approach. And but there is no literature report on so-called on-demand regulation to turn on, okay, or off the emission system. And here we have developed a soft salt based on platinum compound because of the possible platinum interactions in the solid state. So we find that if we ground the sample, the molecules will get closer together so that the platinum interactions will have just one distance in the ground sample. But once you try to restore, okay, by framing with some solvent, then the molecules, okay, will be separate, and there will be more than one type of platinum distance. Okay, for the one with one platinum distance, there will be no excitation wavelength dependence. But for the other case, the emission will depend on the excitation wavelength. So we can actually turn on and off by using this type of approach, okay, by grading or by framing purpose. But this is important to choose the suitable ligand. In this case, okay, you have different separation between platinum center. If we have a very good or bulky ligands on the cyclomethylated ring, okay, so in this case we use our CFE group, which is bulky enough to control the distance between the two platinum center. Okay, so if you have various, okay, platinum distance, then we can control the on and off nature by these two approach. So these are the emission spectrum in solution and also the solid state. And if we increase the fraction of water in the solution, you will see that there is a redshift in the absorption as well as the emission color. And this redshift of the emission is actually due to a larger amount of the soft salt, okay, in a higher water fractions. And from the NMR study, we can also confirm the effect of aggregation. So if you have more water, you see that the NMR signal will become broader and weaker, and which indicates a very significant pi-pi stacking interactions. And for the on state, then if you shine with light with different excitation wavelength, you can see that the emission will show a redshift from green to red. Okay, this is the case with different platinum distance. But if you ground the sample, then you will have a different picture. I will show you in a minute. Okay, and to confirm this phenomenon, we also study the morphology. Okay, by using the microscopy, then we can see that in the aggregated state, it exists as a nanofiber, and the spacing or the width, okay, the thickness are basically the same. So that's why you see that in the aggregated state, with different excitation wavelength, then the emission will be the same. Okay, it is red in color basically. So you cannot see the excitation wavelength dependent emission. Okay, so you can see here, if you grid the sample, then you have same platinum distance. So the change of the excitation wavelength will not affect the emission wavelength. So they are all red. But in this case, okay, the initial case or with filming, then the emission at the beginning will be, okay, in the high energy region. But after that, you will get a single wavelength, okay, the red color. So this is the case for the wavelength dependent situations. And you see that this cycle can be repeated many times, okay? And from the XRD, we can also see that with filming, then the crystal lattice will be more crystalline in nature. But after grading, then the XRD will show very poor, okay, very weak signals. So we can make use of this in the counterfeiting applications. Okay, so with if you control the excitation dependent emission to be off, then no matter what light source you use, they will show you the same color. But you can restore the picture by filming, so that if you use light of different color, then the emission pattern here will be different also. So it is so-called the on state. But you can also control the extent of gridding. Okay, so if you just grid half of it, so the other half, okay, will not change color, but the other one, it will show a color change by using different wavelength for the irradiation. But if you grid all of both the whole picture, the whole pattern, then again, the system will be off. So you have the same color again. So this is a so-called reversible on-off switching of the excitation dependent emission is very unique, okay, in this system by controlling the distance of the platinum separation. And this can serve as a very good anti-counterfeiting label, okay, in security protection. And we also have studied the effect of electric field in controlling the molecular assembly of these platinum complexes. Although it is not a soft salt, okay, but it is ionic in nature. You can see that the effect of electric field can actually shift can actually align the molecules in a very good order. And this can be studied, okay, by using spectroscopy. Okay, we find that the complex show a very good AIEE, okay, the aggregation induced enhanced emission. And this is also supported by some microscopic studies. Actually, with the electric field, then the nano pattern, okay, will change from nano rock to nano flowers. Okay, and this nano flower consists of a bundle of nano ribbons. And can also use the XPS to determine the elements, okay, inside. And this is the stepwise growth mechanism. Okay, you can see how the flower grows up. at different time levels. And finally, I would like to tell you this, okay? If you change the, if you induce the electric field, actually the complex arrangement will be changed, okay, from this to this one, which will account for the nano flower structures. In this case, it will only give you a nano rock structures. And because of this change, we can use the confocal mic or also the lifetime imaging to show the contrast. So this is the PL spectra obtained by the confocal mic. So you can see that the change of color from the rock-like structure to the flower-like structures. And this is also indicated by this image, okay? So you have the green and also the red, yellow, orange, okay? And by using the lifetime imaging, so we can also image the difference, okay, by using the lifetime. Okay, I have tried to tell you how we can make use of the phosphorescent metal complexes in different areas, including the OLEDs and as well as some stimuli responsive materials. And finally, I would like to thank all the people, okay, students and postdoc, as well as collaborators in different parts of the work, and also the financial support from different funding bodies. So this is what I would like to tell you. Thank you.
Thank you, Professor. So I'd like to audience to interact one or two couple of questions to Professor Wong.
Yeah, but I'm sorry, I have to leave very soon. Okay, just I think just 1 or 2 minutes. Okay.
Yeah, 1 or 2 minutes. Yes.
Okay.
भूल गए थे, फिर अचानक याद मतलब 10 बजे याद आया, फिर कॉल किया।
वो रेडी किया होगा शायद ना।
Yeah. Okay, Professor, it was a great talk, and we really had a wonderful time to, have you here, and hope the Indian community, research community, might benefited very well with your enormous, vast knowledge on organometallic chemistry and their application in OLED and biological applications. And we are looking forward to meeting you in the near future in person in India. Thank you so much, Professor, for great.
Okay, thank you.
Thank you. Professor Wong?
Yes.
Thank
Can you hear
Professor.
me?
Yeah. So we will couple of minutes. We will start the presentation. Couple of minutes.
Okay.
Yeah.
बोलना चाहिए ना, क्वेश्चन वो ये किधर गया है?
क्या पता
नहीं हाँ, ये नहीं है वो वेबिनार का जो पोस्टर है ना, है किधर है? वेबिनार का पोस्टर नहीं, उसका बर्थडे था ना, किसका बर्थडे, क्या डांस कर रहे हैं? कहाँ पर आए? कहाँ पे गए?
ये क्या सिप्पू के लैब का
कौन था? किसका बर्थडे था?
सिप्पू का जो था
ये भाई, ये कौन है? रंजिता।
Brother, ready?
बर्थडे के दिन का है क्या? ये रंजिता तो अच्छा टास्क कर लेती है। कौन सा नाम है?
So very good afternoon, everyone. Now we have a third keynote speaker by Professor Wong from National Taiwan University. Now I request Professor Suprata Ghosh, IIT Mandi, to introduce the speaker.
Thank you, Siva, for this opportunity. It's my honor and privilege to introduce our next speaker, Professor Ken Sang Wong. He is quite known in the area of optoelectronics. He received his PhD from National Taiwan University in University of Illinois during the period 1995 to 1996, and University Louis Pasteur Strasbourg in 1996 to 1998. Then he joined the Department of Chemistry, National Taiwan University. Associate professor in 2002 and professor in 2006. His research mainly focuses on the molecular design and organic synthesis of novel pi-conjugated materials for optoelectronics applications such as organic light-emitting diode, electro-generated chemiluminations, solid-state light-emitting electrochemical cells, organic transistors, and photovoltaic devices. Professor Wang.
ये वही है ना
Professor Wang, am I audible? Siva, am I audible?
Yes, you are audible, Subrata.
Yeah.
I think Professor Wong not here. I think. Let me check. He was there. I think the other professor is there. I mean, not in the meeting, but. Wong. Another meeting. Why?
Yeah.
He's in the another meeting. I think you have to tell him to join, otherwise. Only 3 attendees. Professor. Professor, this is Shiva Kumar. Professor. I think you went to the other meeting. You please join in the previous meeting. Please click on the first link. You can leave and then come to other one because we are in the. Just go to the next meeting. I think.
Okay.
Yeah.
And
You can go out and then again join. Yeah.
रेमन वांग ना तो उसके पहले कौन दे रहा है रेमन वांग पहले दिया अभी देगा वांग ये वांग है
I'm not very familiar with this.
Yeah, you can leave. You can leave the meeting and then join in the meet. And then click on that link what we send. First link.
अच्छे से दे रहा ना चुपचाप क्यों करवा दिया वही तो
He left the meeting.
कपड़ा मेड में क्या करना था
But he is a guest. No, already added. No, I think he's supposed to. Whether she can call, we can ask. Sandhya can call. You ask her. Ask Sandhya to call from this meeting where she is there. Yeah, she came.
So I have to use the share button. Is that right?
Yeah. Now we are visible. I mean, no problem. Please share your slide, Professor. I mean.
So Professor Wong, I already have introduced you to the audience. So I now request you to start.
Can you see the slide?
Not yet.
And this?
Share the windows, like screen the.
Are you sharing the screen?
Yeah, I share the screen and I try again. Okay.
Yes, sure, please.
No, it's coming.
Yeah, seems it will work now.
You're able to see.
Is it work?
Yeah. Yes. Please make a full screen and then it works. Your PPT, you make a full screen. Yeah.
Yes.
Yeah, it's visible.
Okay.
It's fine. Absolutely fine.
Okay. Okay, thank you very much. And I would like to take this chance to thank Professor Justin Thomas for his kind invitation to release the webinar on the frontier in organic electronics. So today I'm going to share our recent research progress on the TADF material using intramolecular or intermolecular charge transfer approach. Okay, this is the outline of today's talks. So first, I would like to talk about some background about the OLED technology. And with this very brief introduction, then we will shift to use the intramolecular charge transfer approach for the TADF material. And in this area, we use a very simple approach. Just take the equidin as the donor, then we develop the different types of the TADF material. Then follow this, then I will tell much more about our research approach to use the intermolecular charge transfer approach to make the highly emissive the acid-based TADF material. So, and I will tell about the acid-based as the emitter, and use the very recent developed characterization tool. I'm sorry, because we have a public announcement.
Good afternoon, everyone. We invite Professor Zhang Zhenxian of Columbia University to give a speech at Songbo Lecture Hall around 3:30. Welcome all to the lecture. Thank you.
Okay, sorry about the public announcement. So I will tell you about we used different kinds of the characterization tool to probe the acid-based structure. Then I will tell you about the acid-based as the host for phosphorescence and the fluorescence emitter. Then finally, I will make a conclusion. So this is the very brief introduction about the OLED. Then as you all know, in OLED, the electron and hole recombine, they will generate 25% possibility of the singular exciton. Then singular exciton can emit the fluorescence. Another 75% excitons go to the triplet state. And the pure organic material, the phosphorescence is not emissive. So in principle, we only use these 25% singular exciton to make the device. So the internal quantum efficiency, if you use the pure organic phosphorescence material, you only have 25%. Then combined with the light outcoupling efficiency from the device. So the maximum external quantum efficiency is only 5 to 7.5%. So it's not good enough to have the high efficiency device. Just use the pure organic emitter. So in order to recover the triplet exciton, so they have another approach just to use the material that have a triplet annihilation mechanism. In this case, the triplet and triplet, they will meet each other. This will generate half of the triplet back to the singlet, and they generate the p-type delay fluorescence. In addition to the pumped fluorescence, we can have the internal quantum efficiency about 62.5%. So in this case, the maximum external quantum efficiency we can have is about 16%. Some of the pure organic material like anthracene or the triphenylene hydrocarbon molecule, they have such kinds of the properties. In fact, currently the blue commercial blue the device they are using the material with the triplet annihilation for the blue emission. But as you know, the internal quantum efficiency is not going to 100%. So the second generation, they introduced the transition metal complex. In this case, the spin orbital coupling effect they will relax the selection loop. In this case, the spin orbital coupling also facilitate efficient inter-system crossing. So the single exciton, they are then convert into the triplet exciton and emit the phosphorescence. So we can use the different type of the ligand structure to tune the emission wavelengths from the green to red, even we can have the blue emission. So Professor Raymond won't just tell us that about his very beautiful molecular design and various application use this iridium or some other transition complex. However, this phosphorescence emitter cannot be used as the pure emitter because they have a very strong self-quenching properties. So we have to develop the host material to act as the solid matrix to disperse this emitter. In this regard, my group we developed many bipolar host material, just trying to introduce the pi bridge with the twist structures to separate the hole and the transporting material and the electron transporting material, or we can also use the sigma splitter to completely block the electronic interaction between the whole transporting and the electron transporting functional group. And if you are well designed, then you can also develop the bipolar host material. They are universal, can be used for the different kinds of the phosphorescence emitter. Even you can make the white light emission, use these kinds of the bipolar host. So here are the one of the example to use the highly twisted bridge to separate the donor and acceptor, the whole transporting and the electron transporting material. They have a very weak intramolecular charge transfer to keep the triplet energy as high as the 2.7 electron volt. Another example is to use the sigma spacer to separate the whole transporting carbazole and the cyano-substituted fluorine structure. In this case, we can also keep the triplet energy in a high level. And this bipolar host is also served as the universal host for the different color, even the white light emission OLED. So this is the second generation OLED. But the second generation OLED, they are suffering from the natural resource of the iridium metal. So to make a cost-effective production of the OLED display will be very challenging. So the scientists, they are moving forward to looking for some new material. In this regard, the generation 3 and is to use the TIDF material. As the Professor Adachi tell us the whole story and the recent progress about the TIDF material. And so we know now the basic criteria to reach the TIDF is the energy difference between the singlet and the triplet. If we have a much small energy difference between these two states, and thermal energy is able to convert the triplet exciton back to the singlet, then we have the delay fluorescence from the singlet. In this case, then we can harvest all the electrically generate the exciton to give the 100% internal quantum efficiency. So we also need to consider the singlet back to the ground state or stated strength, and not only about the exchange energy of these two energy level. So fortunately, this kinds of the the requirement is very similar to the molecular design strategy we use for making the bipolar host material. For example, we use the twist pi bridge to separate the donor and acceptor, and also the sigma bridge to completely separate the donor and the acceptor. And actually, we found some of our bipolar host material, and they show the twister, the conformation between the donor and the acceptor, and these bipolar structure, they did perform some TATF properties. So we collaborate with Professor Adachi, and we publish this work. And although the external quantum efficiency is not very high, but they did perform the TATF behavior. Another case is to use the sigma spacer to separate the donor and the acceptor. So this case, they also perform the TATF behavior. But consider these two, the structure, you can see the POQY of this twisted structure or the sigma separate bipolar material. They have a relatively low POQY, that resulting the device with relatively low external quantum efficiency. So not only to consider the exciton utilization efficiency, we call the internal quantum efficiency. So we can make the device, make an emitter, they are able to recover the triplet exciton in the case of the transition metal center emitter or the TATF emitter. But we also need to consider the light coming out from the device. So here is the emitting layer. They have several kinds of the mode. The light restrict the light coming out from the device. So only in this direction they have the light coupling from the device. So another way to improve the device efficiency is to consider the emission dipole of the emitter. If you have the emission dipole emitter, have the vertical emission dipole orientation, and the light will coming out in this direction, not from the emitting layer, out of the device. But if you have the emitter that present the anisotropic emission dipole, particularly in the horizontal orientation, then the light will be much better to come out from the device. So how can we make the molecular emitter, which is such an anisotropic emission dipole behavior? One of the review article published by Professor Yokohama, and he mentioned from this review, the emission dipole orientation is strongly related to the molecular structure. If you have the bulky or compact molecular structure like AOQ3 or these C3 symmetry structures, then they have a much random emission dipole. But if you have the planar or the linear structure, for example, like this molecule, and they are very long and linear, and they have a relatively high horizontal emission dipole. So for designing the highly efficient emitter, we may also to consider the molecule shape, and this shape will affect the ion coupling issue in the device. So we are very happy to collaborate with Professor Adachi and to use our bipolar host and to verify the molecular design strategy that really can perform the TATF material. But we do like to improve the emitter's quantum efficiency. So we just look up the literature. We found out one of the molecule published by Professor Adachi, and they used this as donor structures. And this is the relative stronger donor structure with the oxygen bridge here. And this is the relative flexible donor structure. So we want to restrict the conformation by introducing the much rigid carbon bridge here. and make a much weaker donor structure. In this case, we are able to blue shift the emission, and the new emitter, they can give the much higher POQY as you compare to this model compound. They have a emission wavelength in 540 nanometer. Our new one, they have close to 500 nanometer. But you can see the content yield is much higher compared to the model compound. So with this new emitter, and here we use this device structure, use our bipolar host material, MCPCN, and dope with our new emitter. Then we can have the relatively high the external quantum efficiency. More interestingly, that this molecule, they can use as the pure emitting layer. Even we use the pure emitting layer, we still can have 20% external quantum efficient. That makes us much more confident to move to modify these dimethyl equidin-based structures. So our idea is simply just to introduce a much rigid structure in the carbon bridge from the dimethyl group to the diphenyl group. Then we make another new one is to introduce the much rigid structure, use the spiral equidin case. So here's the crystal structure of these three molecules. As you can see, the dimethyl one and the spiral one, they have a much coplanar structure in the equidin part, and compared to the sided twist with the diphenyl substituted equidin. And this will affect the photoluminescence content yield a lot. As you can see, our the model compound with the dimethyl substitution, they can give the 90% POQY, but the twisted one, they only give us the 82% POQY. And more interested in the rigid spiral equidin one, they can give us 100% POQY. So we use the DFT analysis to analyze the frontier orbital distribution. And this is very important to generate the DFT behavior, because we need very limited overlap between the HOMO and the LUMO orbitals. As you can see from this picture, and the HOMO and the LUMO, they have a limited overlap in this part. Mostly the HOMO are localized on the equidin donor, and the LUMO are localized on the triazine acceptor. In these three cases, they have the very, very similar the orbital overlap and orbital distribution. So we analyze their emission wavelengths, and at very beginning we think that you change the substituting from this carbon bridge doesn't have the effect on their emission wavelengths. However, we found that the emission wavelength is slightly changed. Compared to the dimethyl substituting one, the spiral and the diphenyl substituting one, they have the blue shift emission. So we are interested to see why the substituting group on the saturated carbon bridge, they have such effect and for the blue shift emission. So we use a very simple the C13 MMR to check the chemical shape of this bridge center. We found out this bridge center is the downfield shape to this chemical shape compared to the dimethyl substituted carbon bridge. So we now know this bridge is much electron deficient, and make this spiral equidin is a much weaker donor structure. And this weaker donor will reduce the intramolecular charge transfer, then they have the blue shift emission. And the much weaker electron donating ability of this spiral equidin compared to the dimethyl equidin also can be verified by the cyclic photometry. For example, you can see the dimethyl substituted one, they have a much higher HOMO energy, and also means they have reduced oxidation potential. compared to the spiral equitin-based donor, they have a much higher oxidation potential. So the DMAC and the dimethyl ST1, they have a higher hormone energy compared to the spiral equitin one. And as I just mentioned, the molecule shift they have a very important effect on the emission dipole. And so we used angle-dependent photoluminescence characterization, also used ellipsometry to characterize the absorption behavior of these three molecules. And interestingly, we found out the spiral equitin one, they have much better anisotropic the emission dipole. And by the simulation, then we can calculate the horizontal emission dipole to be 83% compared to the 72% one with the dimethyl substituting one. And so in this case, then this anisotropic the emission dipole can help us to improve the device efficiency. And because this molecule, they have a very high content efficiency, high content yield, and very short delay fluorescence lifetime. And so we use this as the emitter in this device structure, and combining this high POQI and horizontal emission dipole up to 83%. And the theoretical and the external content efficiency can be reached to about 38%. In our device, we can have the external content efficiency reach to about 37%. We can also improve the external content efficiency by introduce the micro lens to enhance the light outcoupling efficiency. So we can improve this external content efficiency to about 63%. So how about this molecule will generate this high anisotropic behavior? It is because we believe that this coplanar arrangement of this aromatic ring will make the molecule arrange in anisotropic behavior. So here the emission dipole is along the molecule long axis, and this molecular arrangement on the emitting material will make the emission dipole in an isotropic way. So the dimethyl equitin look like the very interesting donor. And so we use this as the common donor by introducing different kinds of acceptor into this donor structure to systematically study the structure and property and the device performance relationship. So for the acceptor, sorry, they have the public announcement.
Good afternoon, everyone. We invite Professor Zhang Zhenxian of Wuhan University to give a speech at Songbo Lecture Hall around 3:30. Welcome all to the lecture.
So in this case, we introduce the acceptor with a different number of the nitrogen in the heteroarray structure. Also, we introduced a different number of the electron withdrawing cyano group into this heteroarray to tune the acceptor strength. So here's the molecular calculation and the crystal structure about the dihedral angle between the donor and the phenylene bridge, and the phenylene bridge and the acceptor. So you can see the dihedral angle is well fit to the X-ray structure, the theoretical calculation. And much more interesting is the twisted angle between the phenylene and the heteroarray, and they will affect the orbital distribution. As you can see, and here have the twisting angle compared to here the nitrogen and the phenylene without the also steric interaction. In the bottom case, and here they have a much better contribution to the luminol energy from this phenylene ring. So the common donor structure with the different sector, they can give us a very good example to make this cyclic photometry and to see because we have the common donor, the hormone energy level doesn't change too much, but we tune the acceptor structure, then they affect the luminol energy. For this one, they have two cyano group on the pyridine. They have a much reduced the luminol energy. And for the one with the benzene ring with the cyano group, they have a much higher luminol energy. Of course, the emission wavelengths, you can see they are systematically tuned into the much longer wavelengths with the much stronger acceptor. And also, we check the delay for resonance corrector with the stronger acceptor. They have a much evident delay for resonance corrector. So with this data, we are able to plot and using the reduction potential as the x-axis and different physical properties as the y-axis. As you can see, the emission wavelength is strongly related to the acceptor strength. They will move to a much longer wavelengths compared to the higher reduction potential one. They are in the blue range. And more interestingly, we care about the delta ESD, the energy difference between the single and the triplet. And here you can see the case with much the stronger acceptor, they have a much reduced energy difference between single and triplet. And more importantly, we use this the structure and to correlate to the rate constant. One of the rate constant is the reverse inter-system quotient rate constant. Another one is the additive the rate constant. And we found out very interesting one. If you have a much stronger acceptor, and the reverse inter-system quotient rate is much higher. But the additive rate constant is reduced if you have much stronger the acceptor strength. So we make the device with this the series the emitter and follow these physical properties. Now we know the TIDF emitter with a much stronger acceptor, they can perform the much higher device efficiency. The best one, they can reach better than 30%. So this year we published another work is trying to change the bridge structure here. For example, the bridge structure we shifted from the phenylene into some heteroarray, but using a different number of nitrogen on the bridge the structures. So for this 6 the emitter, we carefully characterize the photophysical properties and electronic properties, trying to find out which one is the best acceptor. And considering the delta EST and the delay for resonance component and the anisotropic behavior, and so we find out this one, the PYOCN with the pyridine as the bridge, and the final part with the phenylene with the 2 cyano group is the best acceptor. So we used this best acceptor coupled to our spiroaquidine In this case, you can expect we can increase the photoluminescence content efficiency. Also, we can increase the anisotropic emission dipole ratio from this anisotropic, the isotropic behavior improved to 7-8% of the anisotropic emission dipole. You can elongate the molecular length into a much linear structure by using this spiral bis equity by introducing the two acceptor to increase the length of the molecules. In this case, you can see we can still keep the emission dipole in the much higher level and to 100%, and but we can also improve the horizontal emission dipole ratio up to 90%. So with this, the high POQI and the high emission dipole, you can expect the device using this spiral bis equity coupled with our new acceptor, they can have the coupled with our new acceptor, then we can have the device with external content efficiency increase to 36%. So these are the some of our example to use the intramolecular charge transfer approach to give you some idea about the molecular design strategy for the high emission TADF emitter. So I would like to switch the gear into the intermolecular charge transfer complex. And in this case, we need two molecules, they meet each other. And if the energy offset between the donor and the acceptor is large, then the electron in the hole, they can confine in at the donor and the acceptor interface. So the electron hole, they have the ability to recombine to generate the emission exciton. This emission exciton we call the excitase. Okay, and this excitase, the emission exciton, they have a well separated HOMO on the donor and the LUMO on the acceptor. Because this well separated HOMO and the LUMO, they have a very small exchange energy. That means that you have a very small delta EST, and this will feasible for the efficiency to reverse intersystem crossing. So how can we make this the excitase system? You need to consider several parameters. For example, you need to consider the suitable energy level for the charge injection from the neighboring group. Okay, and you need to have the donor and the acceptor have the high charging mobility that will lead the electron hole to reach the donor and the acceptor interface. And of course, you need a large energy level offset and to block the electron hole at the interface. And more importantly, you need to have the high triplet energy for both the component donor and acceptor compared to the acceptor emission. So the first case, the acceptors, they demonstrate So this acceptors, the first case is founded by also reported by Professor Adachi, and in this paper, they show these two molecules, they mix each other. They can emit the strongly ratioed emission peak. This emission peak is corresponding to the energy difference between the acceptor LUMO and the HOMO donor. And as you can see, this emission is much low energy compared to the phosphorescence of the donor and the acceptor. You can see the phosphorescence spectrum of the donor and acceptor here. So this is the very important criteria to give the high efficiency on the SIPS system. Although at that time, these two molecules, they can generate the POQI about 26%. But this blend, they can have the device have more than 5% EQE. And this is the groundbreaking report about the SIPC in the OLED. Another interesting feature is the SIPs, they have a slightly redshift delay component compared to the pump component. Okay, and this is a very interesting features. So after then, this paper, then many related work was published in the literature. So we are invited to report a spotlight article on this journal. In this journal, we summarize some progress about the SIPS system and talking about the versatile application of SIPS system, not only for the emitter application, they can also serve as the host material and use the FRET or Dexter energy transfer to the phosphorescence or the TIF emitting systems. That in that case, and SIPS is served as the co-host material. They can also use as the typical fluorescence emitter host. So in our lab, we have a lot of highly efficient electron transporting material. So we are looking for other donor material to pair up with our electron transporting material. One of our electron transporting material we call the POT2T, and here we have a triphenyl phosphine oxide, the electron accepting periodic side group here, combined to a very typical whole transporting material, the carboxyl-based the MCP. So both of the molecule, they have a relatively high triplet energy, and once these two molecules blend together, they can generate the first sky blue SIPS system. And we are very happy to see this result. They also make some effort to tune the device structure by introducing different kinds of the electron transporting material. Here, just use the POT2D itself or other triazine-based electron transporting material. But we find out that this combination is the best one. They can do this sky blue SIPS emission with a relatively high external quantum efficiency. Okay, and POT2T is very versatile. The acceptor, it not only can meet with the high triplet energy MCP to generate a sky blue SIPS system. They can also combine the donor with much higher HOMO energy, like this structure, to generate the yellow SIPS system. So with these two SIPS system, then we make a tandem structure by introducing the blue SIPS here, then with the charge generation there, then stack with this yellow emission SIPS system. Then we are able to make the whole SIPS-based white light emission OLED. This is the first case to use that SIPS into a tandem structure to demonstrate the white light emission. So our purpose is to make the new molecule structures and trying to improve the SIPS, the emission efficiency in the device. So here we demonstrate an interesting strategy. Our idea is to increase the steric interaction on the bridge part. Okay, and if we introduce some stereo group in this part, they will force the acceptor to much close to these donor structures. As you can see, use this very useful acceptor POT2T combined with this carboxyl-based donor, and this one with the steric group, they can improve the external quantity efficiency. So this strategy can also apply to make the green light emission assays. We use also the triazine-based 3N-T2D as the acceptor, and here we introduce a much larger the tribenzyl serial group as the stereo group. So you can see the external quantity efficiency can be also improved from 11% to 13%. Interestingly, we found out the unsymmetric donor, they can have a much better interaction with our POT2T. So, and this unsymmetric donor coupled with the POT2T, they can generate a green light on the SI place. And the device can be fully improved to have the EQE better than 16%. And then we introduced the electron withdrawing group onto this central carboxyl ring. And we found out that we can shift the hormone energy to a much lower level. Then we have the sky blue SIPS system. They can perform the similar external quantity efficiency. So with this cyano group, and we are very interested in our department. My collaborator, Professor Cho, and he's a photophysics, and he developed a very novel characterization protocol, and we call the pump probe, the transient IR spectroscopy. The idea is that we use a pump laser to pump this donor and acceptor mixture, then into the excited state. Then they use the IR to probe the excited state structures. Okay. However, this pump probe, the characterization is the time scale is not able to analyze the singlet and the triplet structure change. But we do find something interesting is that we find out they have a delay component, and it's comparable to the relaxation about 3 microseconds. And this 3 microsecond relaxation is similar to the typical photo characterization we found in other experiments. And we, with this, we also find a much longer delay component, about 14 microseconds. And we assigned this 14 microsecond delay component is coming from the metastable the ground state, and then back to the original ground state. So you can see the energy gap here is much reduced. So we think this can use to explain why the delay component is much redshifted compared to the pump fluorescence. In addition, we also find the formation of a polaron and the radical cation or radical anion in a much comparable time scale. And this observation tells us some very important insight about the SIPS formation and the dissociation of this SIPS acetone into the polaron. And that will tell us that it is impossible to have the 100% of POQY of the SIPS emission, because the SIPS, they have a strong tendency to dissociate into the free polaron. So now we know the POQY of the SIPS system cannot be reached to 100%. So we have to find out some other physical means to improve the SIPS-based OLED efficiency. That is to find out some system they have the S-phase emission with the anisotropic emission dipole. We are very lucky to find out this bis carbazole with this CNT2D mixture. They have the first case of the S-phase with the anisotropic emission dipole. They have the horizontal emission dipole up to 84%. And this blend, they can have the POQY only 64%. But this anisotropic emission dipole will give us a much higher device outcoupling efficiency. So the theoretical device efficiency can be reached to 24%. So in our case, we first generate 21% EQE with this S-phase system. So in 2020, we further improved this S-phase based the system with the device efficiency can be reached to 26%. And so far, this is the world record about the S-phase based OLED efficiency. So in this case, we also study the magnetic photoluminescence properties. In this study, we prove that in S-phase system, the reverse inter-system crossing, they are involved about the spin orbital coupling process. So as I just mentioned, the S-phase system is not only can be used as the emitter, they can also use as the host material. And the singlet and the triplet acetone, they can use the FRET or the Dexter energy transfer to the phosphorescence emitter. Then they can generate much better device efficiency. So we can trap the charge carrier on the S-phase co-host system, then followed by this energy transfer process to give the good device performance. So we collaborate with Professor J.J. Kim and to use our first Sky Blue S-phase system to use the benchmark the iridium complex as the dopant. Then in this case, we can have the very good device efficiency. At that time, this is also the best one. After that, then they switch the MCP into a much larger donor. They call it MCPP. They can also further improve this device efficiency better than the 34%. So not only the phosphorescence emitter can be introduced into the S-phase host, but also the typical fluorescence emitter, they can introduce as the emissive dopant. But in this case, you have to block the Dexter energy transfer because we know the typical fluorescence emitter, the triplet is not emissive. So by reducing the doping concentration, in this case, by introducing this coumarin-based dopant, and this device can reach about 14% EQE. So in our hand, we also do a very similar experiment. And in this case, we also introduce the same dopant. But here we want to demonstrate is in the S-phase co-host system, the electron and hole is freely moved. They have a very good mobility. And we use the transient electroluminescence experiment to introduce the reverse bias to drive the electron and hole back to the electrode. Now, in this case, we can reduce the emission intensity. That means the electron and hole can be freely move in the acceptor and the donor. Also, we find out the S-phase system, they can provide a device with much higher stability. So with this result in mind, and we are also recognize the importance of the NIR and the OLED, as mentioned by Professor Adachi. They have many interesting potential application in the futures. So we use this SFSD system, then trying to introduce this linear fluorescent emitter by changing the central structures to tune the emission wavelengths. So one of the important feature is the emission of the SFSD need to overlap with the absorption of the dopant. So with this, then we are able to demonstrate this deep ray to orange the SFSD host for resonance the device with a relatively high device efficiency compared to the other SFSD system host the case. Our case is a relatively good device performance. But as you can see, the emission wavelengths of this device is not really going to the near IR range. So we need to develop the new the host system by introducing a much higher hormone level donor. And here we use the triaryl amine as the donor center, provide a much higher hormone energy level combined with the CNT2D. They can have the orange to red SFSD emission, and they can also perform relatively good device efficiency. So with this long wavelength, the SFSD emission, then we are able to do the energy transfer to a near IR emitter. Here we have the cyanosalvin as the central group. Then with this emitter, the energy of the SFSD can completely transfer to this dopant with the relatively low doping concentration. And here we have about 90% of the emission is in the near IR1 range. And with this the device structure, then we found out this SFSD host system not only give us the high external quantum efficiency, and more importantly, as I just mentioned, the SFSD host the OLED, they can provide a much better device efficiency compared to the device without the dopant. The dopant can strongly extract all the charge carrier into and then do the efficient energy transfer. So this is the story I'd like to share with you, and today I'd like to make the point about the molecular design strategy for the TADF material. First case, I use the intramolecular charge transfer in order to have the weak couple and donor and the acceptor. And we use the equidin as the donor, use different kinds of acceptor, and trying to find the good TADF emitter. And this is a very good example to extend the molecular length into a much longer one, and they can produce the much better and isotropic emission dipole. Then the second approach is to use the intermolecular charge transfer and trying to find out a different combination between the donor and the acceptor, and they can generate a different emission SI place, and the strategy to improve the SFSD emission, and the physical characterization tool to analyze the SI place structure, also indicate the formation of proton during the relaxation of the SI place excitome. Then finally, most important point here is that we know the SFSD system cannot reach to the 100% PLQI, so we need to find out some new system. They have the anisotropic emission dipole of the SFSD system. Here is the one of the example. They can give us the very good SFSD-based device. And finally, the SFSD system is not only used for the emitter, but they can also use for the host material for phosphorescence for the typical fluorescence. And in this case, we also demonstrate one of the example for the NIR OLED. So this is the final page. I'd like to thank my student and collaborator, and my group is the organic material group that we only make the material. We send to the different collaborator for the device fabrication, and we also collaborate with some photophysics and some physics, and some international collaboration. And I'd like to thank for their effort to make the great work about the TATF material. Here, the founding agent, I also like to thank them for the financial support. Finally, I would like to thank you for your attention.
Thank you, Professor Wong, for excellent talk. And when we see your when we see the whole session, then of your talk, you not only presented a library of some innovative TADF and XIPlex emitters, you nicely explained how structural features tune the optical properties, and also the role of molecular parameters in controlling the emissive performance. So it's really a very good talk, and the floor is open for 1 or 2 questions. So please feel free to ask or raise your hand.
Hello, Professor.
Yes.
Yeah. Sir, good afternoon. Yeah, it was very nice talk. So I have one small curiosity question. So in sky blue XPlex device, you have used rhenium oxide MCP mixture as a, I think, whole injection layer.
Yes.
What is the advantages of this mixture than molybdenum oxide or HATCN like?
Yeah, we typically use the rhenium oxide or molybdenum oxide into the whole injection layer, because we know this metal complex, they have good ability to improve the whole injection into the whole transporting layer.
Okay.
Yeah, so we use the rhenium oxide, or sometimes we use the molybdenum oxide or tungsten oxide, the metal oxide, to improve the whole injection. Yeah.
So which one is better, or all are similar?
It depends on the fabrication plan. Okay, the different group that they perform the different performance of using different metal oxide. It is depending on the fabrication, the vacuum chamber, and the bowl they are to hold the sample. And some of my collaborators, they use the quartz as the bolt, and some use the tungsten as the bolt. The tungsten typically use the tungsten oxide will be better. Then if you use the quartz bolt, then the rhenium oxide is better.
Oh, okay.
Okay.
Yeah. Thank you, Professor.
Thank you.
Is there any other question from audience? Okay, if there is no other question, I thank Professor Wong and
thank you.
Professor Siva Kumar. You have anything to announce, or for Professor Wong?
Okay, thank you. Okay, bye-bye.
Thank you very much.
Professor Wong.
Yes. Yeah. Bye-bye.
Thank you so much for accepting our invitation, Professor.
Yeah, I hope we have some chance to visit you very soon.
Yeah. And
yeah.
unmute just unmute now. Professor Justin is here.
Yeah.
Yeah.
I see him on the screen. Huh?
Yeah, are you able to recognize me? Probably, I think that it's a long time we met.
We never meet each other, huh?
Yeah, sure. Sure. Thank you.
Okay. Yeah, I think that sometime in the future we can meet each other. Yeah.
Sure. Thank you.
Thank you.
Thank you.
Wang,
Okay.
Professor
Bye-bye.
Subrata Ghosh, for your giving time, both of them.
Thanks.
And yeah, we will meet on 3 o'clock for the next talk, Professor Caroline from Germany. So,
okay.
Yeah. Thank you for joining us, everyone.
Good.
Yeah.
Yes, ma'am. Yes.
And Faisal.
Yeah. Hello.
He sent one link
Same
for
link
day
only.
April 1. So they will. Yes. And streams का down.
पहले तो बंद हो जाएगा ना ये उधर है हाँ सीनेट हॉल का ना हाँ उसको अभी लॉक कर देना ना
Yes, will stop immediately. Will no longer be live.
हाँ सेव हो जाएगा
और उसका OBS भी